Hello, everyone, and welcome to Apply. I'm Mike. I'm one of the co-founders and CEO of Tecton. Let me kick off here. So, hope everybody can see my screen here. Welcome to the Apply Community Meetup. It's a pleasure to have everybody join us today. And if you're coming back, this is your second time at Apply, welcome back. It's been just a few months ago, we hosted the first Apply back in April, and it went really well. The motivation for this type of event is really to bring together people who are working on data and ML engineering for production ML. And so we had, when we did the first Apply, we had a group of 40 plus speakers, a bunch of thought leaders. It went really well. The community response really exceeded our expectations. And we had more than 7,000 people register, more than 1,000 attendees, and more than 9 out of 10 people recommended or said they would recommend the event to a friend. So it just went really well. And we really didn't want to wait until another year to run something like that again. So we wanted to bring the community together more regularly, and so that's what we're doing today. We are hosting the Apply Meetup. It's basically a lighter weight version of Apply. And let me just make sure everybody can hear me. I think so. Someone interrupt me if not. But our objective with Apply is to, we're going to do this a couple times a year and have like a more complete conference once a year. I want to thank all of our speakers ahead of time. We have a lot of really great speakers today. We have folks from organizations like Stanford, Shopify, Spotify, Robinhood, Drizzly, just to name a few, and backed by popular demand as well. Dimitrios, who is from the ML Ops community, which is a really great spot. You should check out. He's going to be keeping us engaged during the breaks. So I wanted to just take a moment to kind of reflect on the past year in operational ML and talk about some of the interesting things that we're seeing, and also some of how that relates to some of the work we're doing at Tecton. It's been a really exciting year for operational ML. So we've seen, we're really seeing a mass shift towards this kind of data-centric perspective for building machine learning systems. And that's great because that's really what this community is all about. And as this space matures, we're seeing new tools and abstractions that help make building machine learning pipelines easier and make it easier for teams to collaborate on ML projects. But at the same time, we're doing more complicated things, right? And so these more sophisticated ML projects bring more complex and advanced requirements for ML tooling. And so there's a lot of opportunity for new abstractions and new tools to make ML even easier, faster, and more powerful. So for example, just one example is, data engineering is still where the majority of the complexity lies when putting machine learning applications in production. And this is an area where ML-specific abstractions is having a really big impact in making it a lot easier to do production ML. So I want to kind of just dive into that as an example and see what we can take away from that for the industry overall. So just a quick recap, we know models depend on features derived from the business's data to make good decisions. And there's still a ton of work needed to productionize even the simplest features today. So we've got to connect this data to these models. Even for the simplest feature, like a SQL query that we run against our data warehouse, there's a lot of work to schedule that, run that query against the data warehouse, take that data, load it up into an online key value store for real-time serving for model predictions, save it offline so it can be used for training purposes down the road. And this is just one architecture that someone has to design. But when you have your another feature in your model, maybe one that's like a time window feature that counts how many transactions has a user made in the past 30 minutes. Well, that might happen by aggregating over a data stream. And so that could be a totally different architecture. And often companies that are doing this, they have whole teams built to support each one of these architectures. If you're doing real-time features, if you're trying to extract, for example, like a feature from the search term that the user just typed in interactively into the website, well, you may need a totally other architecture, one that that processes that data in real time. And so, different architectures are needed for different types of features. There's just a lot of data engineering work that needs to happen here. And each of these pipelines has ML specific requirements, right? You've probably heard of a lot of these. Probably a lot of you are working on different, a lot of us are working on different items here. Some big themes are, training, serving, skew, time travel, real-time serving. We've heard a lot of these things before. And there's not really one person that owns this stuff. Because these pipelines touch so many pieces of infrastructure and data science code, it's hard for a single person to manage them, let alone to build them. So one thing that's happening, across ML engineering broadly right now, it's a trend, is that new abstractions are emerging to help people manage these areas of complexity in their ML applications. So for example, for feature pipelines, it's becoming increasingly obvious that teams need a single abstraction to over their features to help them manage the feature pipeline and all of its related infrastructure. And not just like a single feature pipeline, but all of the different feature pipelines that they have in their organization and across the whole ML lifecycle. And so this abstraction is something that we're super bullish about at Tekton and Feast. And we're going all in on this abstraction. So I don't think my slide is updating. Here we go. We're going all in on this abstraction. So we've built a unified feature management layer. So it allows teams to use a simple Python framework to define and register their ML features from these simple definitions, and then have their features be instantiated as productionized feature pipelines. And so the nice thing about this is that then with these new abstraction, we can provide standardized APIs and tools to make these features really useful, right? So to manage and govern these features, to productionize and deploy them, to access their data in a standardized way, to create derivative data sets for model training or model serving, and stuff like monitoring to ensure they're correct over time. Again, this is about creating better interfaces to manage features, not about forcing a specific data tooling under the hood. And so that's why it's really important that all of this operates on top of your existing cloud data infrastructure. So these new ML ops tools that we're beginning to see are not going to be black boxes, but they're going to sit on top of or in your existing data environments rather than introducing a whole variety of new data tools. So in this case, you can have one feature that will be defined potentially, running SQL against your Snowflake, and another feature that can involve running a Spark job against your data lake. And they can be managed in the same way through the same interfaces and also even used in the same models. So this feature platform is a great example of a new abstraction providing ML specific interface that hides a ton of complexity from engineers and data scientists to make their lives easier. And so when using stuff like this, teams get to production faster, they collaborate better, but they also get some other cool stuff. Like they get like the best practice in architectures, for free out of the box, right? And so that kind of saves them time and money. But they also just get much nicer engineering and development workflows, which makes their jobs a lot easier. So this new generation of ML tools is bringing standardization where it didn't previously exist. So this allows for greater decoupling in the machine learning stack. And this really brings like a lot cleaner ML architectures. So for example, with the feature platform, other tools in the ML stack now have a standardized way to access feature data. Tekton offers this through a REST API and Python clients, but this increased pluggability is a great thing for ML teams and not just for these types of platforms. So these new ML abstractions, they really come from teams that are getting their hands dirty, doing this kind of costly shadow engineering work needed in every ML application. So they're the people who are like building ML applications day to day. Fortunately, these teams are the ones that we're going to be hearing from today. The talks today hit on a lot of emerging ideas that are making production ML simpler and easier. And it's an awesome look at what some of the best applied machine learning teams are doing and are developing really to help them run ML effectively in production. So we're super lucky to have an awesome set of speakers today, and I'm thankful to all of them in advance. With that, I'd love to introduce our first speaker. So our meetup kicks off with Karan Goel. He is a third-year PhD student at Stanford. He's advised by Chris Ray, whose lab does some really cool work, and this is an example of it. His main goal is to accelerate the pace at which machine learning can be used robustly and safely in practice across applications and an industry at large. So he leads a project called Robustness Gem, and that's where he builds tools that measure, monitor, and repair machine learning systems interactively. So he's a recipient of the CEPL Foundation Scholarship, and I'll leave it there. Welcome, Karan.
Hi, Mike. We're having a bit of a technical difficulty. We can't get him upgraded, so give us just one more minute.
In the meantime, Mike,
Okay.
I'm just going to come out and say thanks for showing the selfie there of me, huh?
Let's pull it up. Should we pull it up again?
Oh, no. That's what you want to do? All right. I see where you're coming from. That's how
This
that's
is the
how we're
best
going
way
to start this off. That was literally like what, your first slide that you put up?
Yeah. But I think it is a pretty good one. So hold on, let me figure this out. Let me pull it up again.
So that, oh man.
Pretty solid.
So people have already slacked me.
Really?
With a screenshot of that. So yeah, thanks for the embarrassment.
My girlfriend came into when I was preparing these slides the other day, and she's like, "Oh, that's Dimitrios Kewapo."
Oh,
that's an awesome one.
Now I'm gonna blush. So while we're waiting for this, I guess I can call you out on one of your slides then, since we've got this openness going on. I can be radically candor about it. You got to update the Algorithmia one, because I think now they're data robot.
Yes, huge congratulations to the Algorithmia team. They make an awesome product, and they're now part of the data robot team. Yeah, we should update that. I mean, I think they're still Algorithmia. They're just part of the data robot.
Yeah, we got to figure that
community.
out. Yeah. Did they take a different name? We'll ask Diego next time. So the other thing that I was going to mention for everybody out there while we are here talking about this stuff, there's a Slack channel that hopefully everyone is in, Tecton Fee Slack, where we are creating all of the banter for today's whole meetup. And if you are not in it and you're watching on YouTube, or if you're here in Zoom watching, we can drop a link to that Slack. And we encourage everyone to go over there and chat. And also, we may or may not be giving out some swag to people who ask the best questions, or they're the most helpful in that Slack. So keep your fingers on the keyboard. And yeah, I see somebody's asking about the YouTube channel right now. We're broadcasting live on YouTube, and this is also in Zoom, as you probably know. So in case you want the YouTube link, we can put that in the Zoom chat as well. There's a few more updates that I was going to do after Karan came on, but I guess I can do them now, because what is the fun of a virtual conference if there is not a little bit of improvisation? And Mike just bailed on me. All right, Mike, I see how it is. You're just leaving me.
No, I'm here. I thought you wanted to go into updates. I'm here.
It's all right, man. You can go. It was a great presentation. Thank you for that. I appreciate it, and thank you for kicking it off. The updates that we have are, let me collect my train of thought now after I was just talking a little more crap to Mike. All right, so we're on Twitter. We're on Twitter, and we're on social, and we're doing some applied selfies. That's another thing that I will tell you more about in the next break. because I see that things have gone to plan and we got Karan. What's up, man?
Hey, how's it going? Really great to be here. Yeah, I guess it's not an online event without some glitches, so it's good to get them out of the way early.
Yep. Cool, man. Well, I guess we'll kick it off to you.
Welcome.
I'm excited for this.
Awesome. Let me start sharing my screen here. All right, hopefully screen sharing is going okay. All right, I'm gonna proceed as if it is. So, hey everyone,
Yeah,
really
it's all
great
good
to be here. I'm Karan. I am a third-year CS PhD student at Stanford, and I'm going to be talking today about building malleable machine learning systems through measurement, monitoring, and maintenance. A little bit about me. So I obviously come from a research background, so this is going to be a little bit, less from an industry point of view, but hopefully some of the ideas here will translate to things that teams in industry are working on, and we definitely try to work on things that might be interesting to folks in the audience. So let's see how this goes. So let's dive in. I will set some context around kind of the larger, work that I'm doing, and do it by kind of defining this ML software hierarchy, which I think is, my kind of crude attempt at qualifying the different pieces of work out there and what I think is kind of still needs to get worked on. And the idea is that I think of, four blocks here. The first block at the very bottom is the idea of program and run. So this is kind of like standard machine learning. You want to build models and you want to program your data. You want to change your data sets in order to reach a high performing model for some task of interest. And this is kind of the wheelhouse of pretty much traditional machine learning. This is what we got really good at doing over the past 10 years, really. Then there's this layer on top, which is measuring and monitoring what you are deploying or what the models that you've built. And the idea here is that once you've built a model, you want to understand things like distribution shift, because models typically are not working on static data. Data evolves over time, and so models will degrade as well. You want to understand what these models actually know, and you want to evaluate where they work well, where they fail. So a lot of these desiderata come up when you actually have good models that you have some hope of deploying, because then and only then do you really care about understanding these more fine-grained gaps in performance. Then the next step is improving and repairing models. So once you can measure and monitor, it becomes easier to understand where you can intervene in order to fix gaps in your models, in order to repair them, in order to iterate on your data, which is a pretty popular thing that has kind of started receiving a little bit more attention recently. And really kind of this third piece is a little bit harder because it requires getting the second piece right, which is measuring and monitoring your models. And lastly, we have this kind of, I would say, top level thing, which is interaction. How do humans and machine learning engineers, data scientists, all of the different personas that you might care about, how do they interact with these systems that encompass a lot of these capabilities that are listed here? So in summary, we're kind of doing this pretty well, but there's a ton of stuff to do in this bucket. And so in this talk in particular, I'm going to talk a little bit about measurement, a little bit about monitoring, a little bit about improving models, and kind of give a taste of kind of these different areas and what we've been doing on the research side, and hopefully conclude with some thoughts on interesting directions that I think could spur some more research in this area. So let's dive in. So I'm going to talk about malleability as a concept, and this is something that I just made up basically. So it's kind of a made up thing, but hopefully it captures some of the things that we might care about with machine learning systems. So loosely speaking, I'll define it as the ability to modify a machine learning system over time in order to perform bug fixes, hit performance targets, meet ethical standards, whatever kind of capabilities you might want out of your system. And the crucial thing here is that we might be able to define some system components that help us really kind of nail down what we might be looking for in this malleable ML system kind of framework. So The desiderata, at least from my point of view, that I'm really interested in is you want these stakeholders that I talked about, machine learning engineers or data scientists or data engineers to be able to interactively measure, so understand fine-grained system capabilities and performance, monitor, track distribution shift or other shifts in your data and its effects over time, and then maintain, which is perform atomic updates to your data and models as data changes or your models degrade or requirements change in your business, whatever it is that that causes some shift. And so malleability broadly, a malleable system would provide you these capabilities and allow you to do all of these different things easily. And hopefully what that does is makes these machine learning systems a little bit more human-centric and a little bit easier for humans to work with. And hopefully what you'll see in a lot of the other talks as well is like people having kind of attempts at defining abstractions and things to achieve some of these goals. And these are certainly not, exhaustive, but there's some things that I think are important in order to make machine learning work in practice. So one thing I'll say here is that most of the knowledge to do some of these things is tacit currently. So a lot of knowledge about how to actually build systems that have these capabilities are kind of things that people have learned over time as they've been building systems and building up that experience. But it's hidden inside a few large organizations, and then they've kind of built tools to do some of this, but it's not really kind of broadly available to anyone to use. And that's where, startups are coming in the last few years, and they're trying to build some of these tools also in open source and make it easier for people to have access to that. But I think part of the effort is actually taking that knowledge that some organizations, maybe say a Google might have, having done this for longer than other people, and then kind of crystallizing it, and of course, like taking the research advances we've had and putting it together in a nice package for folks to use. So with that, let me dive in. So measurement, just to reemphasize, is understanding fine-grained system capabilities and performance. Monitoring is tracking distribution shift and its effects over time. And then maintenance is performing atomic updates to data and models. So this is the summary of what I'll talk about in this presentation. So let's start with measurement. So you can see I drew these arrows at the top for measurement, monitoring, maintenance, and roughly speaking, I do think there's an ordering, because like you have a bottleneck, you can't fix what you don't measure. So you have to be able to first do measurement, and then you can deploy that into monitoring. And then if you can measure properly, then you can take interventions and corrective action in maintenance. So what we need broadly in machine learning is more fine-grained model metrics across critical slices of data. This is generally a good desiderata to understand what models are doing, and it's kind of the first step, I would say, for fine-grained evaluation. And I'm going to touch on one particular work here that I think Mike talked about in his introduction as well, which is Robustness Gym, which is a fine-grained evaluation toolkit that we've been building on the research side. This is work in collaboration with a few folks at Salesforce Research, Stanford, UNC, and we had a demo earlier this year and have a paper out that you can read, and as well as the code. But that's what I'll talk about. And there's a few other works that I mentioned here, which if you're interested in, you can look at. So let's dive in. So Robustness Gym is our attempt at defining a fine-grained evaluation toolkit. And the idea here is that there are a lot of different ways that you might want to evaluate your models. So coming back to the problem of measurement, there are many different ways you can measure what's actually happening to models inside a system, machine learning system. So there are things like looking at critical data slices, looking at concerns that are driven by, let's say, bias or fairness considerations, looking at sensitivity of your models, invariance to input perturbations, so on. So there's a lot of different ways that people in both research and academia and industry try to evaluate models. And the idea was to bring these together under one kind of umbrella toolkit and hopefully give abstractions that are general and kind of allow you to evaluate your models against a few of these. So on the right, we kind of have the output that you might get from Robustness Gym, which is a report that kind of summarizes evaluations. that you can build here. So the summary here is it's a Python toolkit for building evaluations and then generating these summary visualizations, which we call robustness reports that summarize what a model might or might not be good at. So let me give you a quick, kind of a rough walkthrough of this code snippet, just to give you a sense of how it works and what's actually kind of powering this underneath. So I'll just walk you through step by step. You don't have to read this all the way through. So at the top here, we have loading your data and model in. So you just load a standard kind of here, a data set and some model from Hugging Kiss who do great work in kind of consolidating all these models together. And we support currently a bunch of tasks in NLP. So things like text token classification, text generation. And we're also, working on kind of adding vision time series, all of these things. And I'll talk about that a little bit later as well. Next, we have this idea of running processing workflows on your data. So the idea here is you want to use a bunch of site information or a bunch of metadata in order to do your analysis. This is very common. You can think about, an image data set, for example, and then having labels on it or having metadata on it that allows you to filter, group data, and analyze what's happening on these slices of data. So that's what's going on here, which is we're giving you the ability to run kind of out of the box processing workflows for text processing and generating things like activations and embeddings. And then you can store that alongside your data and use that in your analysis. And some of the actual data abstractions here are pretty interesting, and I'll go over them later. But the idea is you get your data and model, you run these processing workflows to get the site information, and then next, you can create your evaluations by just creating this dev bench object, which is basically a box in which you throw a bunch of evaluations in, and then you can pop reports out of it. That's the rough idea here. So here we have a simple example where we create an evaluation that corresponds to a subpopulation of the data. It tries to look at the tokenized text and then find if the text has certain references to horror movies or something like that. So it's a very simple subpopulation. And of course, you can build your own with the abstractions that we provide, or you can use some of the built-ins that we have, which are common ones for text data. And we support a bunch of evaluations, so things like subpopulations or filtering your data, transforming your data in order to perturb it or attack it. You can kind of generate data by curating kind of data sets and then figuring out manually kind of sampling examples and generating them on your own. Like a common kind of pattern is people like to write down examples, especially with text models, to break a model. So all of those things are possible to do here. And then the abstractions are pretty simple. You just kind of throw in your evaluations, whatever they might be, subpopulations, transformations, and then you add a bunch of metrics. And here the dev bench object is kind of the main driver. It supports all of this kind of exploratory evaluation where you can throw in slices, you can quickly kind of search over them, look at what you have in there, quickly inspect and visualize it using our reports, which summarize all of these different types of evaluations and are kind of an attempt at standardizing reporting that spans a bunch of these evaluation types. You can look at our paper if you want to see how we've actually used it for different tasks. And then you can of course save things and reproduce them, which is very important in machine learning workflows typically, so that somebody else can pick up your dev bench, reproduce your results, and then add to it and continue kind of that process of evaluating and understanding these models. So at a high level, that's pretty much it. Load your data model, create your evaluations, evaluate, and then reproduce and save things after creating your reports. So let me go to the next slide, which is an example of a robustness report that we actually generated using the toolkit. And this is a pretty a simple example for a BERT model on a task that I think is generally only people in research seem to care about. But for the sake of just showing a simple example, this is a reasonable task. It's called a natural language inference. And on the left, what we tried to do was kind of show that we can run a bunch of evaluations that other people think were useful as part of this toolkit. So it kind of is our attempt to show you can broadly span a bunch of evaluations and that the toolkit supports all of these. So on the right, what you see here is all those different evaluation types that I talked about. And those are separated in this report. On the left are the different specific evaluations that we ran to generate this report. At the top are all the different metrics you might want to add. So you can kind of add custom metrics and so on. And here, like, for example, just to point something out, we noticed that our BERT model is actually pretty sensitive to keyboard character errors. So it's kind of sensitive to these perturbations in keyboard errors. And maybe this is not something that you might want for, let's say, a dialogue chat bot or something like that. So this is kind of the idea here. Like, these evaluations are generally useful and can map onto an interesting task that you might want to evaluate. And currently what we're doing is, on our GitHub, we are making this process even easier. We're unifying it for a bunch of modalities. And I'll talk about that again, as I said, a little bit later. But currently, you can just go and pip install and use this. And please give us feedback. Obviously, it's a research project, so we'd love to hear more from folks. So this was the piece about measurement. So I think in summary, I'm trying to kind of bring together all these different ways that you can understand a model in one place, and hopefully learn from that to understand how we can do other things better, like monitoring. So monitoring is essentially this idea. Now that we know how to measure things, can we figure out, does performance degrade over time for our model? And what is that performance that the model has? And typically, this happens on unlabeled data. So your model is deployed, it's running on, let's say, production data, and the data is coming in. That data does not have any labels. You don't know, if it's a cat or a dog, but you have to figure out, is my model doing well on that data or not? So that's the problem. And here I'll talk about one work that came out in ICML this year called Mandolin that we worked on. And this paper basically tries to give you the tools to actually calculate these metrics on unlabeled data. And we have code for this in Robustness Gym, as well as an open source code release. So anybody can just go in and use it. It's like one Python file, literally, I think. So pretty easy to download and use. So what's the setting here? So we have a model. We trained it on a train set. We validated it on a validation set. All of that comes from some source distribution of data, P sub S. So that's the distribution that we think our data should come from. And this is kind of standard machine learning. All this is labeled data. We figure out and train our model. We deploy it. And then once we deploy it, we encounter distribution shift. And that's because our target data, the data that's coming into our production model, is coming from a different distribution, P sub T. And so, bad things happen. What we would like to figure out is, given the fact that the target data that we're getting has no labels, how do we evaluate what's happening there, basically? And Mandolin, which is our work, is a user-guided framework to evaluate models using slices of data. So this connects really nicely to what I was talking about in measurement, where I was describing these ways that you can construct these slices. And then in Mandolin, what we were saying is that now that you have those slices, you can put them to use not just evaluating, but also in this monitoring piece. So it's kind of a dual purpose thing where we're giving you an extra capability with that slicing that you're doing. So that's the conceptual idea for why this might be interesting to do. And then let's just kind of round it a little bit. So a slice is just a user-defined grouping of data, just to reemphasize. And here, I've kind of shown 3 slices. So negation. So for example, you might take a text sentence and then say, like, find me if this text sentence has the words not or an apostrophe T or something like that. And then if it does, that's a negation sentence. And I'll say it lies in the slice. Similarly for these other slices that are marked. So basically, if you do this process, what you can get is on your labeled validation set, which you have access to, and it's kind of your in-house dev set, you can produce this matrix, which basically corresponds to, is this example in a slice or not? So this example, the first example, is obviously in the strong sentiment slice because it has the word love, and that's how we're defining it. And so in this way, you can kind of produce this almost a summary of your data in terms of these binary numbers, right? So it's giving you this binary matrix representation of your data. And of course, since this is labeled validation set, you can figure out if your model is actually performing correctly on this or not. So you can get, like, did my model get this right or wrong, and so on. And then you can get an estimate of your source accuracy or your in-house accuracy, which is, here, let's say for argument, like 91%. Now you can do the same thing for your unlabeled deployment or production data. So the reason you can do this is you don't need any labels to run these slicing functions. You can just run them directly and produce these binary representations. And again, what we provide in Mandolin is an approach that relies on importance weighting, which I won't have time to talk about here in detail, but like the idea is we basically look at, how much, we upweight examples that are more likely to appear in the test set or the deployment data, and downweight ones that are not. So for example, if you had 60% of your validation set was, let's say, a male pronoun, so it was kind of heavily male biased, and then on your test set maybe it was 30%, we would want to downweight the amount of emphasis we put on the evaluation on the male slice, and upweight the one on the female slice. So that way we can adjust our scores on our validation set where we have labels, and then get numbers on the target unlabeled test set. So here, for example, we might produce an estimate that's 84%, and that tells us, without using any labels, we think that performance dropped by around 7%. So that's the idea here. And in the paper, we describe, different approaches. We use this for text tasks, vision tasks, and so on. And typically, we would see like either performance at par, and in some cases, we would actually get 5 times more accurate than standard baselines that people use for this type of task. And the real power here is being able to use those slices to basically kind of reduce the dimensionality of your data, make it a lot simpler, and then do these importance weighting approaches, which people use here. But conceptually, the main idea is how do we get metrics on unlabeled data, and this provides you a simple approach to do that. So now that we've talked about measurement monitoring, I want to jump into maintenance, which I think is probably the hardest piece of this. And how do we measure and make fixes to undesirable behavior? So the idea here is, now that you've measured your model, you figured out things aren't going quite as well as you'd like, and you've identified undesirable behavior, what are the ways in which you can actually fix that? And here we have a couple of papers, and the second one I won't talk about it, but it looks at these more data-centric approaches. So things like manipulating your data in order to improve performance when you have heavily unbalanced data. But I'll discuss the first one because I think it's hard and interesting. So this is a paper that we have in NACL this year called Goodwill Hunting. And the background here is named entity linking. So I'll give a quick background so that you understand what's going on. So named entity linking is a task where you want to map strings or text to things in a knowledge base such as Wikipedia. So for example, if you had a sentence like, when did England last win the Football World Cup? What you would hope that this named entity linker does is that it maps England to the English national football team and Football World Cup to the FIFA World Cup. And then you can use this linker as part of a larger system, let's say a downstream system. For example, that system might be a question answering system. So maybe it's trying to answer this question that you asked. And so here it would want to produce the correct answer, which is 1966. And hopefully, if you have a correct NEL, you'll actually more likely to get the right answer, because of course, if you map Football World Cup to the wrong thing, you're not going to get the right answer. So an NEL is pretty important, and it's widely used in industry across things like Siri or like Google Home and all these different things to understand what's actually being said in text. And in this paper, what we tried to do was analyze and then repurpose off-the-shelf systems. So this is really trying to do this end-to-end thing where we took commercial and academic named entity linking systems off the shelf. So we just kind of took them, didn't tweak them in any way, and then analyzed them using Robustness Gym and produced these nice reports that tell us, different behaviors that you can look at in the paper. And then we picked one particular system that we thought was promising and then tried to guide its behavior for a sports question answering application. And so I'll focus on this repurposing piece here. And what we wanted to do here specifically was we had this this kind of error happening in our data, which is you have this sentence, English player, Harry Kane scored a goal in their match against Germany, but Germany was getting mapped to Germany, the country, instead of the German national football team. Because here, obviously from context as a human, you understand that if it says match against Germany, you should map Germany to a football team or sports team of some kind. And of course, Harry Kane is a footballer, so you might be able to figure that out. And so what we tried to do here is actually try to fix this bug in the model in a very targeted way. And why do we want to do this? Because again, if you have a sports QA system, you want to have a model that actually prefers predicting national sports team instead of countries. So that's where you want to guide the behavior a little bit. And what we did was super simple. This is kind of inspired by work in data programming and the Snorkel system, where we relabeled our training set, which was noisy and it was collected from Wikipedia, so it wasn't perfectly labeled in the first place, with a very simple heuristic that was very sports focused. So what we said was, let's try to label, match against sports team as a pattern that generally So match against is a pattern that's generally preceded or succeeded by a sports team type of entity. So that's just a simple training set heuristic that we used, and then we kind of retrained the model. And in the paper, we have kind of a little bit more analysis, but what we saw was like, just with simple tweaks to the data, where you're kind of taking a more data-centric perspective on how you want to tweak your data, you can get pretty large improvements that guide the model towards the desirable behavior. So here we saw, an absolute accuracy improvement of 25% on these sports errors that they particularly care about in a sports QA application. And that's kind of interesting that you can do this in a systematic way for this pretty complex task or pretty complex system of doing named entity linking. So I'm gonna start to wind up here a little bit and talk a little bit about wish list and kind of things that I'm pretty excited about as far as malleability goes, and then I'll conclude with some kind of emerging work that we're doing that I'm pretty excited about. So there's a lot to do in this end-to-end regime of like going from measurement to fixing the problem that you find, and there are a lot of approaches, and some of these approaches we attempted to bucket in the paper, where there's these data-centric approaches that rely on doing data augmentation, collecting more data, doing active sampling, labeling your data, processing your data in different ways. And then there's these more model-centric approaches. And what we've seen is that typically in industry, the experience of people who put models into production is that data-centric approaches tend to be more performant, and they give you more bang for the buck. So that's just in general a pretty interesting kind of separation that we should hopefully study more. And then one thing I'm pretty interested in is understanding how to atomically fix models, so that you can incrementally, like software, kind of keep patching models and hopefully produce a model that covers all the errors that you care about, but you don't have to do it in this kind of slapdash way as we do it today, but more kind of atomically as you would do in software. And of course, like what we want to do is understand, at least in the research side, the trade-offs between these methods, and then talk to folks in industry as we are doing today, and figure out where we can actually make progress on these questions. So that's something that is a wish list from my perspective, and especially on data-centric AI, we're doing some work that I'll mention at the end. One thing I'm super excited about is our project called Meerkat, which is trying to build these data panels for doing interactive machine learning. And so the idea here is, I talked about these 3 different pieces of measurement, monitoring, maintenance, and you need kind of a substrate, a data substrate that allows you to do these things interactively. So I talked about at the beginning this desiderata for malleability, that stakeholders can do these things interactively. And that's where some of the data abstractions that we're trying to build come in. So this is in the Meerkat project. I put a link to a demo at the bottom, but and you can find links to this at the end. But the idea here, in terms of what we're actually trying to do, is, let's say you have a CSV called data.csv that has some data. Typically, you would use pandas to analyze it, but pandas often doesn't work very well for complex data types, and that's where machine learning kind of centric complex data types is where we want to be for this project. So here, what we would do is load in a data panel that has this data, and here what we support is a bunch of different backends in terms of how we actually store and process the data. So for example, let's say the data had image ID, file path, and label. It would get loaded up as this data panel, very much like a pandas data frame, and then you would be able to kind of use it. But what else you can do here is that you can actually define these specialized columns. For example, you can define an image column in Meerkat that basically takes your file path and then recognizes that the column actually contains images, and so you can do image-specific operations on it. Similarly, you can also then run machine learning models and produce columns that know that they contain predictions or that they contain embeddings inside them. And so then what you can do is produce, for example, you can run UMAP on a embedding column and produce a plot that shows you kind of the embeddings and other interesting workflows. So this is kind of still early work. We're still I think maybe 3.5 months in, and we kind of have the first version of this built out. So we would love if people would like to use this. And we're building these interesting workflows. So if you have ideas for workflows you would love to see in a data structure like this, please reach out to us. But one of the things that we did do is actually make Meerkat the backend for Robustness Gym. So now it powers all of that evaluation workflows, all those evaluation workflows that I talked about. So that means that because Meerkat supports different data modalities, we've been able to extend kind of Robustness Gym's capabilities to things like image data and other data types. So that's kind of the the thing that I'm very excited about, which is taking a more data-centric approach to all these different things and a more interactive approach as well to let people work with this data, which in machine learning at least is not just your training data, but also your predictions, your embeddings, and your model and its weight. So all of that it needs to kind of fit together in some data structure and make it easier to work with. So with that, I'm just going to kind of close out, and here's some of the papers that I talked about. I'm just going to put them up. And one resource that I'm pretty excited about that I just want to advertise very quickly is this data-centric AI GitHub repository that we've been building at Hazy Research. And it's just a kind of our attempt at trying to build a community around this area of data-centric AI. And if you go there now, you'll see kind of, it has a bunch of pedagogical value in that it has, a bunch of resources and links and discussion of pretty important areas to data-centric AI. And we would love to have people contributing and kind of putting in whatever you think is interesting in that. So please feel free to go there and check it out. And that's it for me. Thanks so much.
Karan, amazing, man. So one thing I want to ask you before we keep moving, I noticed you called one of these projects Mandolin,
right.
And you may have seen that I'm a bit of a
right,
musician
right.
myself. Where did the inspiration for that name come from?
I can't take credit for it. It was my advisor's idea. I think if I remember correctly, he said, you're working with slicing. And mandolins, he had recently bought one to slice, I think it was cucumbers. So he said, maybe you want to name it a mandolin after the slicer I just got. And it kind of fits the theme of the project because he's working with slicing. But it's not that kind of mandolin. It's a different kind of mandolin. Yeah.
Yeah, I now understand that. Sweet, man. Well, thank you for this. We're going to keep rolling. I really appreciate it. And as always, your shirts are on point. Do you only own Hawaiian shirts?
I own like a ton. I own so many Hawaiian shirts. I own probably 30. It's a bad addiction.
That's awesome. Well,
but they're cheap. So I don't I'm still grateful.
Sweet. Well, next up we have Rand, but before we bring him on, I'm going to give you a few announcements that we've got going on. As I mentioned before, Karan came on. We're having everything in Slack right now. So if you want to ask Karan any questions, jump over to the Slack and ask away. I think he's going to be on there for the next half hour. Maybe he'll even stay an hour or all morning. Who knows? So you've got the Slack. If you are not sure how to get to that Slack, we're posting it in the YouTube chat and the Zoom chat right now so that you can just migrate on over, introduce yourself. We've got 2 channels that are going down in Apply Conference and Apply Conference Networking. And in that Slack, I'm going to put up a poll right now to let you all vote as to what we should do in the next break. So we did 2 things the last Apply conference that people seemed to like, or at least they told me that. Maybe that's a little biased. Nobody, whatever. So the 2 things that we're going to vote on are whether or not we should do a meditation or an improvised song in the next break. I'm going to let you all choose that, and then we're going to do that. The next break is coming up right after we hear from Rand and then Aparna. All right, so let's intro Rand right now. And while we're at it, I did forget to say, yes, we are giving out swag. And yes, you can get some swag by putting up a selfie in Slack or on Twitter and just tag with the hashtag, if it is on Twitter, applied selfie. And next up, I see Rand is already on screen. What's up, dude? How you doing?
How are you?
I'm great, man. So for anyone who does not know who Rand is, he's a senior machine learning engineer at Robinhood, where he focuses on the serving stack and the feature store. Ding, ding, ding. If you are playing drinking games, then now is your turn to drink, because we're going to be saying feature store quite a bit today. Before Robinhood, Rand worked at Google and was also one of the founding engineers of Vertex AI, the feature store product. In this talk, we will, or he will, share the lessons learned when he and Robin Hood built a feature store from Feast. So I will leave it to you, Rand. I'm excited to hear about what you got to say.
Yeah, cool. I'm going to share my screen and also make sure nothing inappropriate pops up. Okay. All right. I guess, can you make sure you can see my screen?
Yep, looking good.
Right. Cool. Yeah. I have been working on feature store for, at least 2 to 3 years. So I'm actually getting tired of speaking feature store. But today, actually, I'm again very excited to talk about the project we do internally, and we want to share the experience how we build a feature store using Feast. A little bit more about myself. I work in the core ML team inside Robinhood. Yeah, and I mostly in charge of the serving stack, like feature serving and the model serving. And for this talk, we will be focusing on the feature part. So before we go into the technical detail, let's ask a question, like, do we really need a feature store in our organization, right? Because when we propose such project to leadership, you cannot just tell them, yeah, I read a blog post and it says like every machine learning team need a feature store, right? While this statement might still be true, we decided to build a feature store from first principle. So one important rationale we have is feature is so important to a machine learning model. And we certainly need some infrastructure to help us to manage them. And also, we noticed there's some communication costs between data scientists and engineers when they try to bring their features online. And there's some more additional part, questions we want to address, like how do you guarantee the correctness? How do you do monitoring, alerting when the feature changes? So with this question in mind, I also want to talk about what we were at before. This diagram that shows before we have this feature store project. So data scientists in charge of the feature extraction, the pipeline, and also the data scientists would be in charge of the model training, because they are the one who build the feature. They know the business logic way much better. So they build a model. And then after they have the model, they would also bring up some model servers. And that's a place where the product team would send requests to. And before the feature store project, the product team actually need to write some kind of loading job, because when data scientists extract the features, they would put the feature in a Hive table. And product team, which is mostly, I'm referring to engineers, they write to this PySpark job to load the features into Redis, and then they would write a client code, because they are the owner of the server. And in the client, they actually would concatenate both the features from Redis and some other additional one that's not available, and send all of them to the model server. And our team actually owns the model serving infrastructure, which is the infra we built first. And as we see, actually, there's some switching between data scientists and product team, and especially for this task, we really actually don't need product team to do any work. Actually, we can build a shared infrastructure to help simplify the process, so that data scientists would manage in the core logic, while the platform would be in charge of the reliability and scalability. And that's why we start to look into the feature store, and specifically Feast. We actually investigate a couple of options, both commercial and open source. We decide that Feast actually is the most compatible with our internal test stack. And it is so modular, so that we can just take some of the component out. And specifically, so what we do is we take out the Feast core and the Feast online serving, and we deploy as it is. So just some kind of environmental variable changes, nothing more. So just deploy as it is. And we actually need to rewrite all the batch ingestion part. And the main reason is we manage our own Spark cluster. So we cannot use the data processing services like AWS EMR. So we don't have the luxury to use that. So we have to rewrite that part in PySpark. And finally, we actually inherited a lot of classes from the Fizz SDK. This will allow us to ingest some custom logic specific to us, while we can reuse most of the code. So it actually greatly reduced our development time. And now we have the feature store up. We are gradually rolling out production traffic. Now, this diagram actually shows like how it looks like what we have today. Yeah, so I will explain this in more details. So the data scientists, before, so they would first still need to do the EDA. This is not related to production. You can do it in a notebook or by some SQL query. So after you decide there's a bunch of features, you want to push that to production, this is where it gets started. So you will first start it by writing something we call feature definition. Basically, you will specify the name of the feature, what's the type of the feature, and also like we allow you to specify a couple of validation rules on how you validate the features. I will talk more in more details later for that part. After the data scientists write a definition, we will deploy that to something we call metadata store. Basically, it's a Fizz call. And we also write some small tools to, for example, we can diff the config locally with the config store in the meta store and show you some like what has been changed since last time. And by doing so, we block some illegal actions. Like you cannot change the name of the feature. You have to create a new one. If you want to delete a feature, you have to go through the deletion process instead. And you cannot change the type of the feature, and you have to add description so that others know what your feature is used for. And then data scientists will still be in charge of the feature transformation pipeline. So because they know the business logic, and it will generate a Hive table, which is stored all the features. But after that will be automated. So we have a Airflow deck that will listen to the Hive table. And once that table is ready, we would read the definitions. Actually, the arrow is wrong. The definition is read from the metadata store. And we would validate the type is right. We also allow downcast if you want to like cast your flow 64 to flow 32. We support that. We also do a bunch of validation. You have to pass those checks before really putting your data into the Redis. And then the ingestion job would automatically put the things into Redis, and that would be made available for online serving. And then next, the data scientists would bring up the model server as before. The only change is they can specify an additional config file. And this config file would allow you to say, okay, this some feature I want to read from Beast. The name is Beast because it is our internal project name, because it's built from Fizz. So now it becomes Beast. So we allow you to specify what feature you should read from Beast. And then there's some pass-through feature, basically something that's not available immediate in the feature store right now. We also have some front-end engineer that's building up the UI for easier registration and discovery. And one part I did not mention is the feature history. So originally we want to maintain some copy of the feature value, but it turns out we actually didn't do that. One of the big reasons is we also do a lot of backfill. And what would happen is if you backfill the Hive table, you also need some way to trigger the ingestion job. They have to remember to do that. This might not be very user-friendly. So we decided to just maintain some kind of pointer to point into the Hive table so that we actually construct, we can go back to the history by query instead of keeping a copy. Yep, so that's roughly how the overall like architecture looks like. And I will go into a little bit deeper. Into some customization we have been doing. I think this part is the most interesting part to me. So due to some like internal infra constraint, we actually cannot do a gRPC to Java services. So we cannot deploy like just the physical as a pod or the fixed serving as a separate pod. So what we ultimately decided is we pack the whole thing into a single pod. Because like physical is pretty lightweight, so we haven't seen any like performance issue. We also have an additional layer. We call it gateway server. Basically, this server in charge of translating gRPC into REST API. And we use a tool called gRPC Gateway that will allow you to generate the Golang code from a protobuf. And the server was written in Dream framework. So by having this additional server, we certainly, like if you have large data, you might see some performance degradation, but it's still fine for online serving. And this also allows us to add like additional logging, monitoring, and the server would also check the health of the two trial process. And next, I was going to talk about the validation rules, as just I mentioned. So we have a bunch of validation rules to help you validate at, like, for example, feature level. So you can specify like, for this particular feature, we don't expect the null ratio to be exceed 20%. And we will check that before every ingestion. And we also have a capability to kind of look back for the past few days partition so that we can say, if there's some changing in the null ratio, we also want to block that and investigate a little bit more. And this is something at feature level. We also have something at the feature table level. A typical one would be the row count. So we want to guarantee some like lower bound and upper bound of the rows stored in the Hive table. So this would guarantee, for example, if there's some bad table generated, you can capture it earlier on. And also the upper bound can serve as a safeguard, so we can estimate the storage right before the ingestion. That can also give us some alert on like we should scale up the Redis cluster storage, or we should scale up the node. So that's something very important. And how user will use that is they would do that in the feature definition. If you're familiar with Fizz SDK, you actually see something like how you define a feature object. You have the name, the type, these are all the same. We just have something in additional, like we allow validation rules. This would actually store inside the metadata field in the proto. Yeah, so we also have a bunch of like new proto buff defining. We call it like Fizz extended. So it's a extended proto, which we will pack all this proto into the metadata field for storage purpose. And then finally, I want to also talk about where we are going. The historical storage part is, as I mentioned, maybe it's not strictly needed, but this is would be still useful for those lock-in based feature, meaning like you can lock the feature at model inference time, and then you can reuse, if you want to reuse that feature back, we certainly need some storage solution for that. We are also doing some customization. For example, we want to have some search endpoint so that I can match the keyword to the description, so that this will support the UI for a better search experience. We are also discussing streaming feature support, but it will not come soon yet. And we're also trying to explore some other storage options like DynamoDB for online serving. And lastly, I think we also have idea like, because now we have a pod storing the gateway server and some other Java process, we are seeing we might need to customize some code in the Java part, which this part can be written in the Golang, but we're still debating on how much effort we should spend on this, because we have a very good relationship with the Fizz community. We have a very good experience working with them. So rewriting seems to be a very costly operation to us. Yeah, and this concludes like some future plans for us. And And finally, yeah, we still have enough time for Q&As to see if there's any questions. But before we go to Q&A, I also want to mention my team is hiring. So if you're interested in building serving stack, training stack, so anything related to machine learning infra, feel free to talk to me over Slack. Yeah, that's all I have.
So I can jump on and ask you a few that I'm seeing coming through in the chat on Slack. And one is which version of Feast are you using?
Yeah, we are still on 0.9.4. So we have an upgrade to 1.x. Yeah.
All right. And how is the learning curve for Feast?
Yeah, I would say so far, let me go back to the diagram. I think we have a pretty good experience using Feast. Specifically, I think it's the modularity. So we can take out some component and we don't need to adopt all of them. And I think William is always there to help. And I think I really appreciate his insight on this. Certainly very good experience working with Feast.
All right. And what happens when feature validation fails? Alert, drop data, fail ingestion, or materialization?
Yeah. So if the validation failed, we would just block the whole ingestion job at that time and pin on call to kind of investigate why. Because so even you have the validation, it still does not guarantee your feature is good. But the validation is something like the bottom line. So you have to pass the validation. And if there's some additional problems, we need to add like additional like monitoring in the serving after the serving to capture. Yeah.
Sweet. There's some good questions coming through here, so I'm going to take a little bit longer, and this might be the last one or second to last one. How many data features do you use for offline and online? Can you provide information about performance for offline and online parts?
Yeah. So right now, I would say we have a few hundred features supporting like 10 models roughly at that scale. We are, for the performance wise, our measurement would be like, if you want to read 400 features, double features, we are seeing P99 at around like 20 milliseconds. So that's something we are seeing. I mean, for a single, for example, a single entity ID or a single user ID, if you call it. For the ingestion part, we are seeing around like, let's say we can say 10 million rows with 100 features that can be done in 1 hour. So we don't have very strict time in the ingestion part, but it certainly meets our need. Especially for the ingestion part, we actually write it ourselves. So yeah, one interesting aspect I didn't mention is, let me go back a little bit. It's actually the ingestion job. Because like for data scientists, what they want is, I want the feature into the Redis as soon as possible. I want to like turn up infinity resource to make sure it just go into Redis, but that's very dangerous. It would occupy a lot of CPU resources, and that would affect your read. So what we do is we actually do quite aggressive throttling, and we limit the job concurrency and resources that you can use for the ingestion, so that we add more security to the Redis cluster.
Well, it looks like he might have froze. Let's give him 1 minute or a few seconds here.
Yeah, I was thinking the I freeze. So.
That was just such a great answer. All right, I think we'll go ahead and wrap up this session. Up next, we'll have ML Observability, critical piece of the ML stack. So we'll go ahead and take a quick break, and we'll see you back here in just a few minutes.
Oh, I'm back.
Oh, never mind, he's back. Welcome to the world of virtual events.
Yes, so that froze. That was awkward. And it looks like we're doing the break, and we're doing a song in the break. And so We can do this song, but here's what I need everyone to do while we are doing the song. In between you asking Rand all these extra questions that you have for him, get into the Apply conference channel and feed me some lyrics. Oh, did I freeze again? Really? Am I free? I'm freezing all over the place, aren't I? I guess it might be trying to push it a little bit. Hopefully this comes back online. Hopefully you can still hear me and I'm not like super frozen. So let's see if this works. For any of the musicians out there, what key should I play in? That is probably the first thing. And I am looking at, just so you know, and I'm probably like super glitchy right now, so forgive me for that. I don't know what is going on with my computer, but you know what they say. As something can go wrong, it will go. I am looking at the Apply conference channel, just the normal one where there's all this good stuff happening. Hopefully you can hear the guitar now. And anybody that is a musician, give me a key. Which key should we be playing in? I'll take that as D or G or B flat. And oh my God. Somebody put G. Okay, cool, good. So I know my visuals are a little bit glitchy, but hopefully you can still hear that. All right. Now I need some lyrics. What are we going to talk about? What are we going to sing about? Karan, he sang and he told me that he was using mandolin, but it wasn't the kind of mandolin I thought it would be. Yes, he was wearing a Hawaiian shirt. It fooled me for a minute. I figured I should put on mine, but then I realized I only have one and it's dirty right now. We're gonna be talking about feature stores, machine learning, and data. Oh, lovely data. Oh, so much data. Don't forget about the goats of machine learning, the greatest of all time. Data distribution shifts. Oh my God, it's making my computer freeze up. All these bugs, but at the end of the day, this is what you're looking for. What you're looking for, we're just doing a break and improvising some songs. 'Cause we love these features, features, features. We love these features. We love them so much, we're gonna put them all in a store. What's the next prediction? I think it's a bug. Ooh, so many bugs in here. I feel like I'm in a swamp. Get me out before we got that training servant skew. I feel like now I need to take a little break and go back to the conference you originally subscribed to. So that's all we've got for now. If you want more, just tell me, 'cause I could do this all day. Actually, I do it every week on the ML Ops community meetup. So that's all we've got. Now, I think we are ready to roll into the next talk. Thank you all for the incredible lyric suggestions. That was amazing. You all are great and chatty. In case you do not know, we're giving away swag, and some of the ways that you can win this swag is by filling out the feedback form and the ML Ops form that we're putting in Slack right now, and we're putting it everywhere. Basically, take the community poll. That is one way. We're going to be choosing 5 or 10, no, I think 10 random people from that poll to get some swag. And in case you're wondering what the swag is going to be, I'll share with you later, but just trust me, it's cool. Just would I lie to you? Really? Do you want to see it? No, Aparna, you're already on. All right, I see it. My computer's going so slow that you're coming up now. I see you already on. Awesome. And another way, just last one, another way for you to get some swag is by posting a selfie for the rest of us to laugh at. You already got to laugh at mine. You saw it in the beginning. Mike was very, very kind in sharing my selfie. So now you share yours. Let's keep it going. And if you want another song, just let us know. And maybe in break 2, we can do another song, or we do the meditation if you all need to chill out. All right, Aparna, what's going on? Hello.
Hello. I don't know how I'm gonna follow you in that song. You had me crack up, so I don't know how I'm gonna follow that, Dimitri.
Well, I mean, I think people came for machine learning stuff more than they came for random people singing out of tune and improvising songs.
It came for machine learning, left with music about data distribution changes.
Exactly. What was it? The training serving skew.
Well, I'll jump in and
I'll leave it to you.
I'll kind of kick off, but the next version of this, I'm gonna have to do it singing. That's the dream now. So I'm gonna have to step up my game.
Yes, I will play backup or do some harmonies.
Awesome. Well, cool. Well, hey everyone, thanks so much for joining. My name is Aparna, and today we'll be talking about ML observability. Well, we're gonna try to do it not singing this time, but next time I got I'll work on it. Brief kind of overview of the talk today. So I'll go over probably pretty quickly just some of the challenges with productionalizing ML and how we think ML observability can play a part in alleviating that. But the majority of the talk, probably most of the meat of the talk, is going to be around what you came for, which is the really the sauce behind all of the ML observability. So how do I monitor, look for things like drift, performance analysis, data quality checks, and explainability. But just so we're all on the same page, we'll kind of take it from the top. And the core reason for ML observability is that journey from research to production is a really hard journey, not just really big companies, but across even startups who are trying to put models into production. And a lot of the questions that folks try to ask during this journey is kind of once a data scientist, let's say, has built a model, exists in a Jupyter notebook, that journey of asking, will this model actually work as I move it into production? Once it's in production, is it doing what it's supposed to be doing? Is it actually working? And if it's not, how do I actually troubleshoot and drill down to what's actually wrong and how do I go fix it so I can improve the model over its lifetime? And some of the common challenges we hear folks struggle with, and especially as these models move into production, is kind of around data drift, performance degradation, model interpretability. How do I explain certain decisions? Data quality issues, so especially if there's upstream data pipelines feeding into these models, model readiness, so comparing multiple different versions of these models and really knowing which one you're putting into productions, the best one or the best candidate. And then lastly, in a ton of the more regulated kind of industries that we talk to, fairness and bias issues are a top concern. And so what I'll do today is kind of briefly kind of talk about where observability and kind of monitoring model performance, we've been seeing it pop up and kind of how it fits into the stack. And the majority of the talk will kind of dig in deeper into just what is it? How do you even start breaking it down? You guys have heard a ton about feature stores, and feature stores really do help you kind of handle the offline online feature transformations, maintain kind of really do improve kind of the flow of actually getting that data into production in the same way that you're actually building it. You may have heard of a model store. There's popular tools like MLflow and weights and biases, which kind of sit at this junction of tracking all the experiments and serving as that central model registry, where we see kind of ML observability playing into its roles really as this kind of valuation or inference store that captures all of the online production logs, but also some of the offline kind of records like training or validation, so that you have this holistic picture of what happened in production, has it shifted or deviated from when it was actually built, and those insights should actually be actionable. So if the model is not performing well in production, are there mitigations or remediations that you can take, such as fall back to an older version of the model or a naive model, or retraining on certain upsampled data sets. And so these insights that are gleaned through observability really should be kind of actionable. And so with that, I'll kind of briefly gloss over kind of where this, what the goal of this evaluation store or it really is to enable ML observability, but it really is kind of tracking kind of these training or validation production data sets stored in this central platform to be able to do things like monitor for data quality, drift, performance degradations using baselines. And then when those things start to degrade or regress in production, providing really granular tools to be able to drill down and do RCA so you can actually improve model performance. And so with that, I'll kind of hop into kind of some of the core pillars around what we actually want to be tracking with observability. And we'll try to touch each of these topics, but if we don't get to them, I'm sure that there will be future talks where we can dive into them. So first up, I'll kind of dive into drift. If you're in ML, you've probably heard about drift at this point. So what is it? Why is it important? Why is there so much talk about this that Dimitrio's singing about it? Drift is really kind of measuring this change in distribution. So you may have something like a reference distribution that could be your training data set. It could be your validation data set. And you're really trying to make sure that the data that the model was actually built on or what you're expecting doesn't deviate too far from this distribution as it's kind of sitting in production. And, the reason it's important to monitor this is models aren't static. They really are dependent on the data that they were trained on. So if you trained on a lot of data, perhaps with people with really great, let's say, FICO scores, but then you release it into production and you're starting to see a wide diversity of different ranges of FICO scores, that's something to know so that you can actually decide, hey, if my model is not performing well in certain segments or certain groups of individuals, because I didn't train on that set of data, helps you actually know, when does that data actually start to deviate in production and when do you actually need to start taking action on it. And one of the common questions that we get is really around, what is a good reference distribution? And to be honest, it really does depend on your specific, scenario. So most folks typically will use something like a training data set. This is what I built on. This is what I'm expecting to see in production. But we've also had folks do things like, hey, my training data sets actually, I'm seeing this is more of an imbalanced class problem. When I train, I actually, oversample for certain types of classes, but I don't really expect to see them in my production data set. And so, or when I'm actually launched in production. And so in their cases, in a lot of imbalanced classes example, they do things like actually, here's the first 30 days that the model is actually launched in production. Or, let me look back kind of 30 days in production or use some kind of test set. And I want that to actually be my reference distribution to compare against. We also have kind of folks who measure drift across different live kind of A/B tests, different versions of their model to actually see, is the traffic that I'm actually sending to both versions fair? Is one receiving a different distribution than another? And so really the reference distribution that you want to set does depend on kind of what signals that you want to glean from kind of the shift between these two distributions. And I'll give you just a quick example because we all talk about drift, but what does it actually mean? Like, how do you actually calculate it? Typically, what you'll do is kind of, let's say you have a feature in your model, maybe it's purpose of a loan. So you can get a loan for a car, you can get a loan for a credit card. And what you're doing is kind of looking at how much of your distribution actually falls into kind of your distribution in production versus your reference. So let's just say your reference is, the orange distribution, what's happening in production is kind of blue. You're actually looking into how much kind of percent of volume falls into each of these categories, taking the difference, the natural log, and then summing up kind of all of the PSIs across all of these different categories to get kind of one number that indicates what's the total kind of, shift between these two distributions. And PSI is just kind of one example metric, stands for Population Stability Index. It's actually a symmetric version of KL divergence, if you guys have heard of that. But there's a lot of different metrics for how folks actually measure drift. This is one that's proven to be, pretty stable across numerical and categorical distributions, but there's other ways like Wasserstein distance, Jensen-Shannon. And so lots of different approaches for how you can actually calculate drift between two distributions. But drift isn't an end all, it's not a panacea. So it's good for things like noticing, hey, one distribution has massively shifted, or I'm starting to notice some unseen new inputs. So I'll give you an example. Before the pandemic started, these were actually one of the more popular social media or kind of marketing channels, Twitter, Facebook, Instagram, YouTube. And then over the pandemic, we actually saw something like TikTok boom up, and a lot of folks started seeing that they were getting incoming, it was an incoming channel for them. And so this would be an example of something where drift can actually, it's not going to catch things like, ideally hard failures. It's really more for these kind of slow bleed, things are changing over time. Let me catch them. But anything that's related to kind of a single prediction or a single inference at a time. So things like outlier detection, or if you're looking at data consistency between offline and online, if you're using a feature store, those types of metrics are really not meant for drift. And drift is ideally not the right metric to actually catch those kind of insights. But pretty good metric, especially if you don't have actuals or ground truth, to actually get a proxy for, have things shifted? Do they need my attention? And with that, I'll actually hop into kind of one of the next pillars. So let's say you're monitoring drift. Another key pillar across the board is kind of performance monitoring of the model itself. We see there's really two different cases that we see. One is there's models that get back ground truth relatively quick after they make a prediction. So if I'm at Uber and I'm predicting something like, hey, here's the ETA that I'm predicting for my ride, maybe within, an hour or so max, I should get back kind of what was the actual pickup time, what was the actual wait time. And so I can get back kind of this fast mapping between here's what I predicted, here's what I was actually able to match it with, join them, and actually calculate performance metrics. But in a lot of real world cases, we see, I'd say we see this isn't, it's not always guaranteed to get back actuals in kind of a relatively near-term window. There's kind of a case where, especially with a lot of, I'd say the lending use cases, et cetera, there's a lot where you kind of have a prediction, will this person, let's say, default or not? And you might not find out for several months afterward that, whether this person actually paid off the loan or whether, there was a late payment, et cetera. And so you're actually sitting there waiting in some cases 2-3 months, et cetera, to actually get back the actuals to map it back to the predictions. In this case, what we've seen people do is use things like proxy metrics. So, were they late on the first payment, or, how much is left on the loan? And so metrics like that to give some indication around how likely is this person actually to kind of match what's happening with what I predicted. There's a second case that we see, sometimes these are not mutually exclusive, but we call them kind of biased actuals, where you may actually make a prediction, like I'm going to decide to approve this person for a loan, where I'm going to decide to deny this person for a loan, but you might only get back actuals for a certain segment of your predictions. And so in this case, only people that have actually said, I'm going to approve for a loan, I'm going to get back any insights around kind of, should we approve them? When we approve them, did they not default? Were we right or were we wrong? People that we decided to deny, they really become part of this unmeasurable set that we really have very little indication about how they're actually doing. Would my model, if I denied them, would they've actually, not defaulted? And so what we've seen some teams do is actually have things like, maybe they have a threshold where they decide to approve or deny, but they, test out, thresholds that are slightly below, just to give some indication around what would have actually happened if we adjusted the threshold based off of user actions. And then lastly, we hear folks around few or very little ground truth where, I'll give you a funny example. There's some, folks out there who actually predict things like mortality rates for, do I give this person an insurance, or not? And, in those cases, you can't sit there waiting for years to actually figure out, do I actually need to, am I actually going to be right or wrong about this specific prediction? And so in those cases, they try to corroborate them with other, predictive systems or actually kind of use, business metrics or KPI metrics instead of actually model performance metrics. But regardless of kind of how you're getting back the actuals, I think the same kind of common principle around, similar to traditional DevOps or kind of data observability, you're not just looking at things like aggregate metrics, like what's my overall accuracy or what's my overall precision recall, or you see, however you're measuring performance for your model, really is kind of looking at specific segments and understanding, maybe my model is doing really well on individuals with high net worth, but on people that have actually recently defaulted, my model is actually not that great on figuring that out, or has really low, poor performance on this specific segment. And so to actually know how to go improve the model performance, figuring out kind of what are the subslices, what are the segments where your model is not doing well, is actually what's going to move the needle on improving performance. I'll go through this in kind of a minute and then kind of wrap up. Bad data quality is probably across the board one of the common things that we hear. And there's different ways that we've seen kind of, people handle this. In some cases, let's say I'm just missing a value. Age is one of my features in my model, and I'm just missing kind of what's the age of this individual. We've seen kind of people handle that in a couple different ways. Either decide to drop the prediction request if it's a really critical feature or important input that they actually need to kind of make a decision. Some cases, there may be some imputation. So let me predict or kind of guesstimate or set a default value that might end up, potentially introducing things like drift or data leakage if done improperly. And in other cases, just, do nothing, kind of let the service handle it themselves. In either of these cases, we've kind of seen there's different consequences, and it's kind of a trade-off to decide how do you want to handle missing or bad production data values. And typically the best way to kind of keep a guard on these is to have common checks on things like missing data, out of range violations for numerical values, cardinality, as well as type mismatch, so that you can actually check if certain features are kind of changing types unexpectedly. Cool. Well, I think we're getting close to kind of the end of this particular session, but there's a lot deep that we can go into observability. Hopefully this gives you guys kind of an intro into all of the depth of the space, and feel free to reach out if you have any questions about ML observability.
Super awesome stuff, Aparna. I love it. And please ask questions in Slack. I think, Aparna, you're going to be hanging out for a little bit, answering questions and clarifying some of the stuff you're talking about in this. So feel free to ask the questions in Slack right now. One person posted a selfie. That means that person has really good odds of winning some swag. If nobody else posts a selfie, that person, it doesn't matter what the selfie looks like, that person is winning some swag. So we're going to keep cruising onto the panel right now. It feels like this is going really fast. I guess it's the way that we set it up. We architected it. So we're going super fast. And now we have a huge panel, an epic panel coming up. in case you all did not see the flyer, who do we got coming on this panel? We've got Lex, we've got Neil, we've got Jana. The leader of the panel is Alex. Alex Williams, welcome. If anyone does not know him, the founder of the New Stack. If you do not know the New Stack, get over there to thenewstack.com. Check that out. It is a great place to learn from. And then last but not least, who I did not mention before, Kevin. And if I know one thing about Kevin, when I interviewed him, the wildest quirk that he has is that he enjoys running hundreds of miles in a hot desert. What is going on with that, Kevin? I still do not understand why you like that. And I want to ask Lex one thing before I kick it over to you, Alex. I mean, Lex, I don't know if you were here before. You saw my musical talent. You're working at Spotify. You think maybe...
Contact me after.
Yeah. All right. Perfect. There we go. All right. It's all yours, Alex.
Great. Yeah. I'll wait for the playlist, Demetrius. That'll be entertaining for sure. I want to just thank everyone for attending this presentation today, and in particular, our presenters, our panel. And one of the big focus we want to talk about is really, what is ML Ops? How is it an emerging discipline? How do we think about engineering teams, engineering processes and organizations? And how do we adapt? How do we adapt to operational ML? And I want to start it off with Lex Beatty of Spotify. And just for everyone's benefit, Lex, maybe you could just tell us a little bit about yourself and what you do at Spotify. That'd be helpful.
Sure. Yeah, I'd love to. So hello, I'm Lex. I work as the ML engagement lead on our ML platform team. I started this team about a year ago, and within that time, I've worked with 40 different teams across Spotify, instilling best practices in ML ops, and also how to implement ML in new and impactful ways. The team has grown to 3 people now, which is super exciting. And it's been a great ride.
I bet it has. Spotify, I'm probably like everyone here. I use it every day, and I find the intuitiveness just one reason why. It's just very easy to use, and it gets me the music I like to hear. I wanted to ask you, Lex, one of the things we talked about when we were having a warm-up discussion, we were talking about how the maturity of an organization really affects how you think about ML and how you think about ML ops. And it's still really kind of a jack of all trades kind of a work. So in that context, I'm curious about how ML ops is reflected at Spotify. How is it becoming a discipline? Even though it is still a jack of all trades kind of a work, where it still has that kind of very much of that fiber, that that underlying requirement to be a data scientist to some extent.
Sure. So I think touching upon the maturity standpoint, as your company starts to get into machine learning, you're going to have different needs from where Spotify is at. In the beginning, you might just be working with a data engineer and a data scientist and working on more experimental ML. But once you start getting to a point where you need to scale up complicated practices, then you may need to have an ML ops team or somebody helping to build those types of tools. So that's where Spotify's at right now, where we have an ML platform team where we help build out tools for the ML engineers across Spotify. And we try and make sure that they have the tools they need to be able to do their jobs without having to focus on the nitty-gritty stuff of, trying to make sure they're scaling up properly or making sure that they're using the right tooling, and a lot of the overhead that comes with creating a machine learning process.
Cool. I thought I'd jump in as well, since Lex mentioned that not all companies are like Spotify. I work at a much smaller startup called Monzo Bank in the UK, and we've just made the leap from having generalist data science. That's what the company was like when I joined, that you're a data scientist, you do everything. If Airflow is broken, you fix Airflow. If someone needs some analytics, you do some of that. All the way through to now we hire specific roles like analytics engineering and machine learning separately. So we are not there yet as having MLOps as a discipline inside the company, but we're sort of setting the foundations there about thinking, how can we keep our machine learning scientists as productive and as impactful as possible? And I think we have some other companies represented here. Kevin, were you former Uber?
That's right. Yeah, I was at Uber beforehand, where we definitely did implement MLOps practices. And before I explain that in more detail, I think I just want to quickly define like what is MLOps even, and how is it different to DevOps? And so for DevOps, really high level, it makes it super easy to build and deploy software applications at the end of the day, right? Like you've got the tooling and the processes in place to very easily compile and test and bundle up and version control and deploy and monitor a software application. And now it's super easy for a software engineer to change a line of code, get somebody else to review a pull request. And then once that's approved, things get merged in and you've got this whole pipeline, this whole automation, just push things in a really safe and controlled way into production. And that's what we want to accomplish in machine learning now too. And that's what, in my mind, MLOps stands for, where you want to make it super easy to develop and deploy ML applications. And what's quite tricky here is that when you look at software engineering in isolation, you only have to take care of productionizing and developing one specific asset type that eventually lands in production. That's your software application, like your microservice Docker container. For machine learning, it's really three different assets. You've got on the one side, of course, your machine learning model that needs to be built, trained, and then runs into production. Second, you need to have data pipelines that need to be built, developed, and deployed to production. So you've got data assets available that you can make predictions against. And then third, of course, similar to software engineering beforehand, you still need to have a software application that's built and deployed and runs in production that actually uses the model to make a prediction that then impacts the end user. And so it's a much more intricate and much more complex web of components that need to be developed and deployed in synchronicity, if that's the right English word for it. And that's really what MLOps is about. And we're not fully there yet. I think some organizations like Uber, and I'm sure Spotify to a big extent too, and some other very advanced tech companies have accomplished a lot on this path. But for a lot of other companies, we're still on the path to getting them to that beautiful, fully automated vision.
Well said, Kevin. So just to extend on that, I actually look at the evolution of MLOps as a parallel to the evolution of software engineering. So in software engineering, we have an artifact, which is the binary. So here we have the model. There we have the continuous integration and continuous delivery. Here we have continuous training and continuous inference. And that is the ultimate goal of any MLOps pipeline. We need to close the loop between production and training. So there is a lot of parallels drawn between traditional software engineering and the emerging MLOps and the whole ML engineering. What is interesting is there is, just like there is quite a bit of an intersection of dev and ops in DevOps, there is quite a bit of an intersection between existing DevOps and the emerging MLOps. So it can't exist in isolation. This is taking the best practices of DevOps and Agile and bringing it to how ML is being operationalized and productionized. So think of this as a new parallel stream that is emerging based on the best practices of what we have learned over the decades of doing software engineering the right way.
Doing it the right way. And that leads to me a question for you, Kevin, when you're thinking about how MLOps is different from traditional DevOps. I think Johnny kind of hits on that a little bit. But what does that mean for your teams? What does it mean for your processes? What does that mean for the organization itself? People are used to continuous delivery. They're not used to continuous training.
For sure. The first thing that it means for an organization that wants to use machine learning in the production system is to recognize, okay, now this is actually machine learning running in the production system where it's directly affecting your user experience. So you'll have mission critical SLAs. The system cannot go down. It needs to respond very, very quickly. And that's different to how ML is otherwise applied in many organizations, where it's more on the analytical side, where you're developing, say, reports that the execs see or some dashboards or stuff like that. That is much less mission critical. And so first, it requires an organization to recognize that, hey, this is now a mission critical application. And as a result of that, we want to treat it the same way that we treat other systems that are mission critical and that are running in production. And so, as I just mentioned, you should apply the software engineering best practices here around DevOps, which gives you all the things like version control, full reproducibility, lineage, the ability to monitor the health of your system, the ability to roll it back. That type of stuff is all now required for an ML application. And you need the tooling that is able to take an ML application that you've coded up and now automate the pipeline of building it, testing it, deploying it to production, and monitoring it. All of that is now required. And on top of that, what you also need to have is you need to have somebody who's deeply technical, because at the end of the day, you have an ML model running in production. And I think it is, as of today, still very, very important that you have somebody who's able to actually look at the production system, who's able to debug what's going on, what's going wrong. And so I think as of today, you still need to have a data scientist partner up with someone who's deeply technical and familiar with DevOps principles, DevOps systems, software engineering, and whatnot. And in some organizations, there could be an ML engineer, but not every organization does have an ML engineer.
Johnny, what are your thoughts on that? Does that jive with what you're thinking? You know, what you're hearing? I mean, you work in teams. You've been working with teams who are developing ML ops, and you're seeing differences, I think, between the large organizations and the smaller organizations. And you've mentioned that, you know, before in our conversations. What are some of the distinctions that you see?
Sure. So, you know, just like any other engineering practice, initially it's going to be an all-in-one role. You know, I'm actually seeing one individual owning up a lot of roles and responsibilities. They are handling everything from data science, which is all about experimentation, to operationalizing, which is engineering, to even sometimes building and training models and deploying them and even monitoring them. But obviously, as the scale and the maturity increases, this individuals' roles and responsibilities are broken into multiple, and there are going to be multiple roles and responsibilities, multiple practices, multiple job functions. All of them will evolve, and there are well-defined roles that will own the three pillars of this entire pipeline. The first one is all about data science and data engineering, where we need infrastructure to explore data, prepare the data sets at scale. Then the second pillar is all about creating the infrastructure and the platform for building experimentation and training models. And the third pillar is the infrastructure and the platform layer for operationalizing, hosting, monitoring, and managing models. So what I'm actually saying is these are the three pillars that are acting as the anchors for individual teams to define their objectives, roles, and responsibilities. And everything is aligned with that.
As we just chatted about a couple different roles that are involved here, one thing that I'd like to highlight again, mention, and the folks who saw the intro call that Mike, my co-founder here, TechTon, gave is what we believe is going to be really, really important when it comes to productionizing ML is that different personas of different skill set and roles, like a data scientist and a data engineer and ML engineer, that they can collaborate using the same tools, the same platforms, and the same abstractions. Like that's what we believe is critical to make this move towards elegant ML ops really, really successful. Because right now you've got these different roles working in disparate environments, using disparate tools where you have to have these long handoffs that are error prone, where a lot of boilerplate code needs to be written. And that's required because they're all working in different tools. The data scientist works in the Jupyter Notebook. The ML engineer is an expert of Kubernetes and Java and building production scalable systems. And I believe, and we here at Tectone believe, that we need to get to a place where you, in ML ops, build these platforms and tools that surface abstractions that the different roles and responsibilities involved in ML can get behind and can understand and can collaborate around. At Tecton, of course, we've got for instance, the feature view abstraction and concept that allows data scientists and data engineers to collaborate and work together on data and features that are required for machine learning. But to give you another analogy from software engineering, of course, I think most of you probably know about the Docker abstraction that's made it much easier for software engineers and for DevOps engineers to collaborate on like one shared abstraction of what an application, what a software engineering application should look like that is well isolated and that can run in production.
You know, that's an interesting.
So Kevin,
that's an interesting segue.
Yeah, Alex,
Johnny, maybe you can
I
talk
just want
about
to-
container technologies.
not just container, but one observation that I made when it comes to, again, the maturity of DevOps versus the budding nature of MLOps. So over a period of time, we have identified the tool chain for DevOps, and now it's very mature. There is a source code control, and then there is a blue-green canary deployment at the other end of the pipeline. And there are very well set of curated tools that come into the play to create the CI/CD and DevOps pipelines. But unfortunately, MLOps is in a nascent stage where it is extremely difficult to handpick these tools and assemble the perfect MLOps chain. That is very fragmented, it's very nascent, and it has a long way to go before it attains the maturity of DevOps.
I completely agree. So I think one of the problems that we run into is that there's so much tooling that's available, and there's so many different options that you can take to figure out what type of ML process you want to have for your teams and what types of ML ops process you want to have. And that's something that we think about a lot on ML platform. And within Spotify, since we're more on the mature side, we're able to build special processes around these types of tools. But not every single team can do that or has the resources to do that. So I think it's a really interesting question of what type of tool can you use to do every step of the ML ops workflow? I'd be curious if the other panelists have like tooling preferences.
I can jump in a little bit. In that I'm often on the receiving end of pitches for new tools and startups that want me to try out their tools. So what I'm looking for is that right now in a lot of the tooling landscape, there's a huge focus on how ML ops is different and how it's unique and how there's completely different challenges. What I would aspire to instead is for these differences to one day vanish, right? Because if you go to distributed system engineers who are building a microservice-based backend infrastructure, the sort of problems that they deal with are really not that dissimilar from the kind of things that we want to achieve with machine learning, which is like receive a request and send back something sensible, or like do this for all of our customers right now. So when it comes to tooling, in that end, before I ever go out and look externally for Monzo on what tooling should we bring in, I think what tooling are the backend engineers already using, and what is the very small delta between what they already do and is already supported by platform teams, and what is it that we need as machine learning scientists. So very simple example from our side is that the Monzo backend is built in Go, and we did not want to re-implement ML frameworks from Python to Go. And so the little delta was we just want to be able to deploy Python microservices as backend engineers deploy Go microservices. And with that, we get we don't have to build a completely different stack. We don't have to worry about it. And we're sort of standing on the shoulders of giants. We have this sort of remarkable platform team who think about our Kubernetes cluster. And so the level of abstraction that my team is dealing with is above that, rather than another vertical beside it. So I agree, there's huge tool overload. But my sense right now is I'd rather MLOps and DevOps become one, rather than us focus always on how they're different and unique from one another.
That's so interesting. One of the questions I have is like, how have you just determined that you actually need machine learning at all?
So a bit of context for Monzo is we are a bank, and it's an app-only bank. And if you're excited about machine learning, then I would really encourage you to look at the fintech space in general. It is the entire realm of possibilities, ranging from the same sort of problems you would find in a startup dealing with a purely customer facing product, all the way through to problems that require deep insight and deep domain expertise for highly regulated environments. So yeah, how do we know if we need machine learning at all? Oftentimes we don't. And we oftentimes will not start there. We know we need machine learning when that machine learning would give us a substantial improvement over what we already have. And
has it provided a substantial improvement?
Yeah.
And in what way?
Yeah. So I guess a great example is in our customer operations. So we run all of our customer service via chat in the app, majority of it. Our customers can also email us and call us. And scaling that is an incredibly hard problem. And so this is where machine learning can unlock a variety of opportunities, ranging from helping customers self-service and helping them find the help that they need, all the way through to giving smart recommendations to the agents on how to reply to customers, and even the other side of the coin of machine learning on analyzing the conversational data that we have and figuring out what our customers are talking to us about and what are the trends and patterns there. So yeah, all of these things would not have even been possible with within the realm of traditional engineering.
So that's going to lead me to my follow-up question. We're coming up to the end of our time here, but maybe Lex and Kevin, you could just talk briefly, like, how you started, your journey. How did you know you needed to embark upon, using machine learning, for instance, a service of scale such as Spotify? What is it that led it to it, and does that help fill in the gaps once you know that you have to pursue something to gain more efficiencies or whatever the objective might be? Does that help fill in the gaps of helping you move towards ML ops? And Kevin, I'd like to get your feedback on that too before we finish up.
Yeah, so at Spotify, I was definitely not the first person to use machine learning.
Yeah, right.
I came in a little bit later, and but I do help teams that are just starting within their ML journey to use ML. And one of the first questions that always comes up is, do we really need to do this?
Yeah.
Because if I'm being honest, machine learning is very expensive. It's a lot to maintain and build and test and experiment with. And so you only really want to do it if you absolutely need it. And I think Neil said something about that, where it's like, you want it to be worth that type of investment. So one of the things that I help teams do is go throughout their processes and see where there's opportunities for this type of machine learning. Sometimes we say yes. A lot of times we find out that a simpler answer is easier. So I would say always try to go with the simplest model and then move up.
Yeah, the simplest model typically is just a human hand engineered heuristic, right? It's like a rule that you've got running in production. That's how most people start out with. And like at Uber back in 2014, 15, when it was a really, really fast growing company, just amassing tons and tons of amount of data, it was fairly obvious that machine learning could make a huge difference and replace a lot of the heuristics and rule driven systems. And a good indicator is typically if you're making a ton of repeated decisions based on input data. And if you could later on look back at, hey, did I make a good decision or did I make a bad decision? Like hyper recommendation systems, personalization systems, fraud detection, pricing, all the type of stuff where you're just constantly making decisions based on input data, and where you may today just have a rule implemented that is, that just has a hard-coded decision tree basically implemented. That's oftentimes a good candidate to look at and improve upon with machine learning.
Johnny, is this your kind of practice too when you're thinking about working with teams?
Absolutely. I completely agree with Lex. ML is the most expensive initiative to take up, and do it only if you absolutely need it.
So that's why you need ops, is because it gets expensive, I guess, doesn't it? Isn't that
Absolutely.
really basic?
And the tooling gets the cost down over time, right? Like that's what a lot of the companies talking here, this community and us are working on, to really bring down the activation energy and the cost to apply machine learning. Like,
and then you got to go back to the tooling and spend a lot of time with the tooling, don't you, Neil? I mean, that's a lot of your time.
Yeah, but as Kevin says, hopefully each time you invest in tooling, then the next time you don't have to start from scratch again. I guess one thought here is in sort of analytics and data science, we talk about analysis paralysis. I hope that in MLOps, we're not going to reach a similar like MLOps tooling paralysis. The guidance I always give to teams is get your machine learning over the line and prove that it's actually delivering value to your customers, and then kind of go back and start again and do that twice or three times, and then it'll become clear to you where the tooling requirements that you have are. That was exactly the case with why we built our feature store. It was because we shipped our first model that was using tabular data from our analytics, and then we shipped our second, and then we said, hey, this looks like it's something that we want to do, and we want to increase our rate of experimentation here, and we want to reduce the cost of having to set up that infrastructure every time. So we didn't stop and say, wait, we can't ship any of these models until we have a feature store. We did it the other way around. We said, let's prove that there's value here first, and then go back and see what are the tools that are available out there, the concepts that we could either adopt or build that would accelerate our rate of experimentation.
Well, great. Well, I think it's time to meditate on what we've learned here, and Demetrius is going to do that. But Neil, Kevin, Lexi, Johnny, thank you so much for participating. Neil's with Monza Bank, Kevin is with the Tecton team, Lex with Spotify, and Johnny's just the technologist, media analyst of all trades. So thank you all for your participation today. This has been a lot of fun.
Thanks for having us.
Thank you.
Thank you.
Demetrius,
All right.
back to you.
Cool, Alex. Thanks. That was awesome. I appreciate it. And yes, no one asked for a meditation, but we are going to do it. That's how we are thinking about it. No, I'm going to give away some swag. I get to feel like Oprah for a few minutes right now because there's been some good stuff going on, albeit a little bit of chatter. I would like to see more chatter considering how many attendees we have right now. So hopefully by giving away a little swag right now, it's going to make others want to get and be active and get some swag. So in case you don't know what exactly we're giving away, I should probably show you that. Uh-oh, did I freeze again? So let me just share what exactly we're going to be giving away. Here is the swag right now. Can you all hope? And I'm sharing the wrong thing. Stop, share that. That's the event tracker. that were the plan. Let me share the right one this time, which is this. Please work. And I don't know if I'm sharing the right one or not.
You are. I can see it.
Yeah, cool. All right, good. So now I get to give away some of this stuff. Arise from the Arise AI team, Aparna, thank you for giving us some cool totes bags. Then we got some socks. We've also got some cool stuff from Tecton, of course. First up, first winner here. This is where I get to do the you get a car for a great question in Slack. Joanne Perron, forgive me if I spell the name wrong. You get some swag, so reach out to me on Slack and I will direct you to the right person. Congratulations on that one for a great question asked. Next up, we got another great question from Kailash. Kailash, again, reach out to me. You win some socks and tote bags and water bottles and all that good stuff. So next up is the best/only applied selfie. And that goes to Reed Martian. You win. Congratulations, because you were the only one that put a selfie, the only one who had the audacity to put a selfie. So congratulations, you win.
And
Next,
D, you are not in present mode, so we can see the rest of your computer. So if you want to click present, then we can have full screen.
you see everything. No, that hopefully there was nothing too bad on there. So next up, we've got, this is the last one actually. And this is the best rogue, model gone rogue story. So Jess Dobner, you win because of your model gone rogue story. And the story is, let me just get out of the sharing mode. And so I can find the different story. What was it? It is, yes, we had a model gone rogue. The wrong labels were applied to model logits, producing the inverse of predicted labels we wanted. So basically, the exact opposite of what you wanted to happen happened. And I'm sure we all feel for you there. That probably is not the only time that has happened to some of us that are listening. And hopefully it is the last though, because we learn from your mistakes. Now, Jess, reach out to me. Congratulations. Thanks for filling out the form. Again, we're giving out stuff all day. I only gave out 3 so far. We got to give out like 20 different things. So I'm looking for things to give out. Ask some questions in Slack or tell me some funny things to talk about in Slack. Whatever you feel like, just be active in Slack. I'm not asking for much. I don't ask for much. Come on now. Let's talk about what's coming up next because we are a little bit behind on time. So it was supposed to be a full-on break right now, but since we're behind on time, I think we're just going to go right into it. And we're going to talk with Emily Hawkins of Drizzly. So Emily, if you're around and want to come and join me right now and say hi. Yes, there you are. What's happening, Emily?
Hey, Dimitri. Excited to be here.
Nice. So you're based in Boston. You've got a Master's of Science in Business Analytics from Bentley University, and you've been working in data for the past 6 years, heavily involved in the modern data stack community, working with tools like Snowflake, Dagster, Fivetran, DBT, Looker, and maybe some Tecton, I guess. So let's hear what you got to tell us. This is going to be a short 10-minute lightning talk, and then we're going to jump over to Willem. I'll hand it over to you now, Emily.
Thanks so much for that intro. I'm going to share my slides. All right, so today I'm going to go over Drizzly's streaming architecture. There's a lot of tools listed here, so hopefully we can learn something new. So I'm going to go quickly over analytics at Drizzly, touch on our batch infrastructure since that affected a lot of our decisions around our streaming infrastructure, go through our current use case and architecture, and then touch on some next steps that involve Tekton. So jumping into analytics at Drizzly, this is what our analytics org chart looks like. So under analytics, we have data infra, business intelligence, marketing analytics, and data science. We also work really closely with our data engineering team. Of course, they're the ones setting up, standing up all of this infrastructure, though they don't sit underneath the analytics umbrella. So this is kind of like our philosophy around building out our data platform. I work really closely with our data engineering team to build out this data platform that anyone who wants to use data at Drizzly can access data from. So this includes our data pipelines, our BI tools, our batch infrastructure, data science and machine learning, as well as our real-time infrastructure that I'll touch on today. So jumping in quickly to batch, as Dimitri mentioned, we are really leaning into the modern data stack. We've been building this out for the past 2 years. So we're on Snowflake for our data warehouse, and we use dbt to manage all of our data transformations in Snowflake. All right, so getting into the good stuff with real-time infrastructure. So first, I want to touch on like why we're doing this, why we need real-time in the first place. So I'm going to start off with an example. So say you're hanging out with some friends, you're having some drinks, but you're running low, you need to stock up. So you open the Drizzly app, you add some White Claw to your cart because that's everybody's favorite summer drink. And then you get distracted by one of your friends and you forget to check out. So some time goes by and Drizzly reminds you, hey, you have something in your cart, don't forget to check out. So we currently have this process in place, but it's on a 24-hour cadence. So if I don't check out, I'm not going to get a notification until the next day. And that's not really a great process right now because in a day later, I'm probably not going to really need those drinks anymore. So this is where the real-time infrastructure comes in. With our new setup, we're planning to have these notifications go out on a 30-minute cadence. So if you add something to cart 30 minutes later, you don't check out, we're going to nudge you with a notification to remind you to check out. Hopefully you're still in that moment where it's needed. So we're hoping to see a really big improvement there. So this kind of seems like an easy problem when I explain it that way, but it's actually pretty complex to solve in the real-time space. So for one, triggering on the absence of an event is pretty hard, and that's what we're trying to do here. So someone has an add to cart event, but they don't have a checkout event following in 30 minutes. Originally, we were looking to solve this with KSQL since we're using Confluent Cloud, but unfortunately, we couldn't really solve this problem with KSQL alone just due to limitations on joins and things like that were possible with KSQL. Thankfully, we already use dbt and we were introduced to Materialize. Using these tools together, we can much more easily solve these sorts of problems. So this is what our infrastructure looks like. We have Confluent Cloud managing our schema registries and Kafka topics. So going through kind of the abandoned cart use case here, we would have add to cart and checkout events coming in to these topics, which would then be read into these source objects in Materialize. dbt would manage all of the materialized views, which are pretty much just SQL queries where we're writing SQL to join the data how we need, to transform the data how we need, to apply any sort of logic. to say, yes, this user has an abandoned cart. Once we have that, we can send data out of Materialize using a sync object, which writes back to another topic, which then can be read by any sort of outbound service, in this case, sending notifications to the users who have that abandoned cart. So why Materialize? As I mentioned, we can write real-time SQL pretty much exactly the same as we already are in Snowflake with batch. So it was a much lower barrier to entry. Again, touching on DBT compatibility, we love using DBT on the analytics team, and it was a huge plus for us that we could continue using it for our real-time platform. Again, with DBT, we can centralize that logic in one place, similar to how we are for batch. And applications can either connect directly to Materialize, or as I showed earlier, we can use those sync objects to send data out with like event-driven workflows. In keeping with DBT, we really love that we're going to be able to have a streaming DBT project along with our batch DBT project, where we can follow basically the same sets of standards that we already have in place. Analysts and data scientists are already using DBT on a day-to-day basis, so the ramp up for moving over to real-time analytics should be relatively easy. And again, deploying a real-time model should be as easy as just writing a SQL query. All right, so getting into what we're looking forward to doing next. We're really excited to bring Tekton into our stack for our feature store. So with our real-time setup here, we can see that we can not only bring data in to Tekton from Snowflake, we can also start to utilize some real-time features with our Confluent Materialize DBT setup. So we don't actually need this for our abandoned cart use case, but we'll need it going forward for some other use cases we have in mind. So that's what I have here with abandoned browse. So in this use case, we'll actually want to be setting up some machine learning models to do some predictions on if someone abandons browse on Drizzly, we can predict, say, the top couple items they might have been most interested in based on their browsing experience, based on their past behavior, and be able to send them a little nudge notification on, highlighting those specific items that we think they might be most likely to purchase. So where are we going? V1 is where we are right now. Again, limited personalization. We're not really utilizing any sort of data science model quite yet, but this was really our POC phase. We're learning these tools. We're setting them up for the first time. V2 is kind of what I just touched on with abandoned browse. So starting to implement some more data science modeling in the mix, predicting, as I mentioned, say the top 3 items someone might have been interested in based on their session and past purchases. And then looking forward even more, we think this can actually feed directly onto real-time dynamic experiences on Drizzly. So, say someone is browsing on Drizzly, they're looking at wine pretty heavily for the first time. Maybe we can trigger some sort of quiz and get their wine preferences and then return some recommendations to help them along with their purchase. So that was really quick, but that is all I have. If you have any questions, definitely reach out in Slack. I'll be hanging out there for a little bit to answer any questions anyone might have.
Awesome. There are some questions that have already been coming through. And so for everyone that has been curious enough to ask these questions, please throw them over to the Slack chat so Emily can put them or give you long and very thoughtful answers. Thanks Emily for this awesome talk and super interesting. I really like what Drizzly's doing. I think we're going to keep moving because I managed to take up a lot of time mumbling and singing and playing music. We are going to go straight in to Willem's talk. You may know Willem because he is the creator of Feast. And in case anybody does not know, I'm just going to give a shameless plug for Willem and I. We created a podcast where we talk a lot about Feast, and I'll drop a link to that in the chat. It is really cool to be able to have Willem as my co-host because he's very smart, if you didn't know that already, and he gets to ask the hard questions, the technical questions, and I get to just bring the fun and light vibes. So I'll drop that in the chat. Willem, I'm going to hand it over to you right now. Welcome, man. Good to see you again.
Hey, D. Thanks for having me. Let me just share my screen. You guys can see this, right? Cool. So hello, everybody. My name is Willem. As D introed me, I'm an engineering lead here at Tekton. I'm mostly focused on Feast and the open source project of Feast. And today I'll be talking a bit about using Feast on AWS. So just a quick summary of what Feast is for those of you who don't know. Feast is an open source feature store for machine learning. Basically, we're trying to solve some of the key operational challenges with productionizing data for ML, things like tracking and managing features and defining them as they're used for models in production. How do you deploy, manage infrastructure for serving features at scale, whether it's for training models or for low latency predictions? How do you avoid pitfalls like in data for ML, like label leakage or ensuring point-in-time correctness? And then ultimately ensuring that models see a consistent view of data, whether for training and serving, and in order to avoid things like training serving skew. So those are some of the areas that we've been focusing on with Feast. The whole space of operational data for ML is massive and a lot of problems to be solved, but those are some of the things that we've been working on in the last couple of months. So I'm super excited to announce today that Feast 0.12 is out. We've added 2 new capabilities to Feast in 0.12. The first one is AWS support. So we've got support for Redshift as the offline store, and we've got support for DynamoDB as the online store. And on the right there, I've got a little code snippet. It's a feature store YAML. Essentially, this is how you configure Feast. And all you need to do to make use of this new functionality is, set your online store to DynamoDB, set your offline store to Redshift, add some config fields. But basically, that's it, and you can start using, Feast on AWS. Another thing we added is a new concept called feature services, and this is an important functionality that basically it's a grouping of features that exist within your feature registry already, feature views, as they're used by models for consumption purposes. And this builds a relationship between the features in the feature store and models in production, and it is a convenient abstraction for querying features from the consumption side, where you don't have to provide the whole list of features to query. You can just provide the feature service name, and so that abstraction really helps from the consumption side as well. So what I'm going to be demoing today is Feast on AWS. And one of the things we've heard a lot from teams is, now I've got all these ETL pipelines and Spark and Airflow, and I'm producing all this feature data, and I'm sitting with it on Parquet on S3. How can I use that with Feast? So one of the ways you can do that is, now that we have support for Redshift, is you can add those data sources on S3 as tables in Redshift using Redshift Spectrum, and you can use Feast as the query layer in order to access that data. So what I'm going to show you today is how you can deploy a feature repository that maps those data sources, those features that you're creating from your ETL pipelines, into the feature store and configure your feature store. And then we're going to train a model, and Feast is going to handle all of the training data set creation. And then finally, we're going to ship that model into quote unquote prod, and then use DynamoDB as the online feature store to read feature values, low latency, and make a prediction in order to rank some drivers. So those are the 3 steps that we're going to be doing today in this mini demo. So let me quickly just show you what the data looks like. I hope you can still see my screen. So basically, this is just an S3 interface, Parquet files in S3. This is typically what a team would have, like just some data being produced from ETL pipelines. There's like Parquet partition files. There's nothing special here, very vanilla. So what I've done here is I've created a table in Spectrum that maps the S3 data into Redshift. So Redshift has an awareness of the data in S3. So S3 is the source of truth, but Redshift is going to be our query engine to access this data. And if you look at the columns in this table, it's time series data, it's keyed on a driver, and there are various feature columns like conversion rate, acceptance rate, and average daily trips. And these features are what you want to use to train your model and make your predictions. And so this is already set up, it's outside of Feast, but we need to give Feast an awareness of this data in order to use it for operationalizing your existing feature data. So how do we do that? Well, step one is we want to set up our feature repository and we want to deploy our feature store. So the first thing we do is we go to the feature store YAML file over here, which we've created, and we've set it up already. It's got a provider as AWS. It's got the online store as DynamoDB. And then we've set the offline store to Redshift. And I've configured this already to point to this cluster that we have that can access those S3 files. So now Feast has an awareness of the infrastructure, but what about the business logic? So in order to define or tell Feast where your data lives and the properties of your data, you create a driver repo. And this driver repo has a few objects within it. It's all Python based. But the first thing is you define an entity, which is just a reusable, essentially a key for this driver that's used during the join process when you have multiple sources of data. But in this case, we only have that one table, that Parquet file, that driver statistics, and it's in Redshift. And I've just created this Redshift data source, and I'm selecting that data, and I'm telling Feast, this is where you can find the data. You can just query this table, But how you tell Feast exactly how this data is structured is using a feature view, and that's ultimately how you bring all these things together. Feature view is the ultimate grouping of the data, and it defines the properties and tells Feast how it can treat this data in order to do its point-in-time joins. But that's a cataloging concept. What we're actually going to be using for retrieval is a feature service. Now, this feature service is going to be a mapping of our model to the features it needs. In this case, we only have one feature view, this driver statistics feature view, but you could have many feature views here that you're querying for this specific model. And Feast will intelligently join those together and ensure that your model sees the right data. So now that our driver repo is set up and we've got our feature store YAML, all we need to do is go over into this folder and run Feast apply. And hopefully this works. Right, and so what just happened? Right, if you look at this repository, a little registry DB has been created. What this is doing is just creating a snapshot of the data in the registry and registering like these objects, these entity, the feature view, the feature service. In a production setup, this would be centralized and many teams would share this registry. For this demo, I'm just using a local registry so that you can just see it and it's more responsive. Well, another thing that Feast Apply did is it actually set up our infrastructure like DynamoDB and Redshift in such a way that, and it validated the infrastructure that we could actually use it as our feature store. But so the steps succeeded. Now, the next step is we want to train a model. So how do we do that? Now that we have our feature store set up, that was step one. Now we're moving to step two. We go to this train script. And in this little script, we just want to export data from the feature store in order to train a model, and then use a little linear regression scikit-learn model to train and export a model. And so how we do this is we use, if you look at over here, this driver model feature service as the query. And this query is being fed into a feature store object, and we use the get historical features method on the feature store object in order to query data. And so how this will work is, the feature store object, which was, sorry, I skipped this a bit, defined using this feature store constructor. It knows based on your feature repository where your infrastructure is. It knows which feature views exist, where Redshift is defined, where all the components live. And so when we run get historical features, Feast will generate a large query, send that to Redshift, and it'll query the S3 objects and join them intelligently in a point-in-time correct way. And it knows which features you want for your model because you've defined this feature service already. So let me just quickly run that.
Willem, while you're running that, can you also make the font bigger for us?
I think that would be a little bit tricky to do. I can try and go into presentation mode, but I would not be able to navigate, unfortunately.
Okay, no worries.
Okay, so maybe you can just try and go with my verbal explanation. So basically, you can just create a feature store object, get your historical features. Feast will deal with all the joins. It'll query your backend, your offline store, build the training data set, and train your model. And you can see on the left here, we've created this model. Final step. Now we want to materialize data into the online store and use that for prediction. So we just go over to the driver ranking, our feature repo, run materialize. And now what we're doing is querying Redshift for the latest feature values, loading that into our online store. And how do we make a prediction? Well, it's pretty simple. We have a little prediction script here. What we're going to be receiving is a list of IDs, and we want to, enrich those IDs with features, predict, which driver is the best driver, and return the best driver. So what we do in production is we'd load the model, using whatever tools you already use. But then instead of just querying the online store directly, we instead of like writing scripts like SQL queries as part of our online stack, we'd use Feast as the interface. So you create a feature store object again, just like in the offline case, and then your predict method, you'd use the get online features method instead of get historical features. And in this case, we're querying DynamoDB, and we're sending a list of driver IDs. We're using the feature service that we've previously defined, and we're getting the latest feature values. And then we're using that to make a prediction and then return the best driver. And so if we run Python predict, you should see a driver ID come back. Yep, we got the driver ID back. And so that's pretty much it. I'll share this code with everybody after this talk, and you can see exactly what I meant if the font was a little bit too small for you to see right now. So that's pretty much what I wanted to demo. And what we did is we deployed a feature store with our feature repo that we defined. We built this training data set, trained a model. We use that model then to make a prediction using DynamoDB's the feature values that we've loaded into DynamoDB. So pretty simple stuff. That's all I wanted to demo. Feast 0.12 is out. You can install it with pip install Feast. Our announcement blog post is up in the URL that's on screen. And finally, check out our docs if you want to see more information about 0.12, and come and say hello in Slack. Join the community. That's it.
Excellent. Thank you, Willem. There we go. I am on the screen now, I think. I appreciate that talk, and it looks like Feast is coming along nicely. So congrats on that. We're going to keep cruising. We've got only a half day this time, so we got to be quick. Next up is everyone's favorite, James Campbell. James, if you are around, I am going to ask you to come to the stage. And I'm also going to ask you, I think I sent you a LinkedIn request about 6 months ago asking if you wanted to do an MLOps community talk, and I haven't heard back from you, man.
Oh my goodness, I got put on the spot.
I can understand if you don't check like LinkedIn that much or anything, or you get flooded with requests. I understand, but maybe we can talk after this since we formally met each other now.
Absolutely, I'd love it.
So anyone who doesn't know James, he's the CTO of Superconductor, which is the company behind Great Expectations, which I'm sure a lot of you have heard of. Great Expectations has a solid name and a solid community behind it. And that is why I wanted you to come on the MLOps community and talk about it. So James, I'm going to just give it over to you, man. I'm excited to hear what you have to say, and dare I say, I have great expectations for this talk.
I love that joke every single time.
Everybody says it, don't they? Oh man, I just fell right into the trap. Damn it. So that's all I got. I'm going to just get off the screen now, slowly disappear into the bushes.
Thank you so much for the introduction and for the chance to be here. I'm really excited to be talking about something that's absolutely brand new for Great Expectations, but a feature I'm really excited about. So this is sort of the soft launch preview release that you're getting to see here. And that's exploratory data analysis with a new feature called rule-based profilers. really quick, just about superconductive. We're the team behind Great Expectations. For me, what you're about to see is very, very near and dear to my heart because it really helps with blending quantitative and qualitative analysis, which is where I've spent most of my career in finding ways that we can improve communication between teams that are primarily focused on their subject matter expertise as they're supporting decision making, and teams that are quantitatively driven and model driven, like your ML teams. Great Expectations, just to give a little bit of language what we're going to be talking about, focuses on bringing the discipline and practice of software testing to the data environment. And what you're going to see when we talk about exploratory data analysis is very much in this language, this expectation-centric language that is a hallmark of Great Expectations. So we provide this declarative grammar that starts with things like expect the column to exist, these very schema-oriented, high-level characteristics, and progresses into more semantically rich expectations about data, looking at their specific values or distributions of values over columns. We talk a lot about a variety of different benefits. The beauty for rule-based profilers really comes down to two things. First is underscoring the translation layer between expectations about data and these natural language sentence representations of them that we create. And I'll talk for a second more, a little bit about sort of the history of exploratory data analysis, but the next big benefit is that we're providing checklists of questions. So again, these are two things that we've talked about for a long time of like why Great Expectations is useful, but we're really right at an inflection point in how that works. So exploratory data analysis is a term I think that we talk about a lot in the broader ML field, but going back to John Tukey's book, which, you know, he was just very revolutionary in a lot of different aspects of things that he did in the statistics community. But he took this very interesting approach to how we look at data and was trying to get people away from the notion of data as hypothesis testing and instead provoke a broader range of questions about how the data that we already have can be used, how it can be understood differently, what sort of hypotheses it might suggest that weren't already there to, you know, we weren't already going to test, and then critically, what other data to go get. And a lot of that is done through a very visual language where you're kind of letting the data talk to you. So how does that translate over into questions? I think what I've realized is a lot of times when you're first starting out on an ML project or you're a new person joining a project, you get down, you connect to the feature store, you see what you have, but you need to understand, what does it mean? Like, what are all the characteristics of these features or columns that I have available to me as I'm doing something? And often that looks very much like a kind of flowchart of questions. It starts off with this, like, what does my data look like? And, in Great Expectations, usually we think about it as then moving to these normative questions, like, does it look like it should? What does my data look like? That could usually be decomposed, right? Does it have null values it shouldn't? Is it distributed correctly, and so forth? But each of those have these more factually oriented questions that sit right behind them and that answer the normative question. So with rule-based profiling, what we're doing is we're really foregrounding all of those questions, and we're making it possible to effectively script out, but at a kind of a very semantic level, a general thesis for how you should go about looking at a new data set. And then that's something that you can compose, share, manipulate easily with your team. There are three key things that are, I think, really neat and kind of different in how we're doing rule-based profilers from how previous generations of profilers have worked. The first is that they're configuration driven. So like, this could be hopefully I think you can think of this as a very good thing, because it means you're not in the realm of thinking about having to code things when you want to make a change to what the questions that you're going to ask are. At the same time, they're very customizable. So that could be that you're changing just the configuration, but it's also easy to slot in additional components. So if you have a different kind of way of generating a histogram or a plot or some other metric that you think is very important for your approach to doing exploratory analysis, no problem, you can put that in. And then lastly, they're very reusable. All right, very high level. I've got a little bit of snippet. Let me switch now and take a look at a notebook. So in this notebook, what I'm doing is I'm going to actually go through the process of running and explore one of these rule-based profilers and then take a look at what we see as a result. And I think what I'm hoping to do in this is really trigger, aha, there are all sorts of things I want to do next. So first, we're firing up a data connector. And if you're familiar with Great Expectations, this will be very familiar. And if you're not, it's very, kind of boilerplate. We're just basically providing access to one of the public, very common data sets, New York City taxi trip data. And then we have this profiler, and each profiler is composed of a number of rules. Rules take the form of a domain builder or something that describes the part of the data set that we're going to describe. Expectation configuration builder. So the things that will define expectations, and then optionally, but critically for the story we're telling, these parameter builders, which are the things that go through and identify metrics. And so the thing that's really interesting that's going on here in this numeric range or metric range multi-batch parameter builder, wow, longest name ever, is that we're getting past just looking at the metric, and we're actually looking at a distribution of these metrics over some number of batches. So in this case, we're looking at the previous 11 months of data, looking at how over those months of data, the value in question, whether that's the row count or min values or max values, how that has been distributed. And then we're choosing a value based on a target false positive rate that will give us a picture sort of what the likely range of these values is. Really quick, last thing is I just want to show sort of what is some resulting elements of that. And so I've got a couple examples. First is an example of running the very basic kind of schema level profiler script against this taxi data and then validating it. So critically different than previous generations, or different than a lot of these kinds of systems. Instead of being purely descriptive, we're describing on some large number of batches of data and inferring on some large number of batches of data, and then also looking at how our most recent data compares to that. And we can immediately just sort of at a glance get a picture of what kind of thing we're looking at, what kind of characteristics the data has. And then, of course, the thing that makes it really exciting is when we look inside of something and we start putting up the kind of classic Tukey distribution plots or box plots. In this case, this is just a histogram, of course. But critically, instead of just being of the observed values, we're able to start comparing and looking over time at how our data is changing, all from this very simple scripting interface. So there's my super fast lightning version. And I think for me, what I'm super excited about here is that what we're trying to do is provide a framework that makes it possible to share entire workflows for how you go about exploratory analysis, and make it easier for people to jump in on a team, get right into the process of understanding a brand new data set, and then share those insights with other people and start locking them into expectations that can inform all their future work.
Amazing. James, thank you for that, man. That was awesome. Really exciting stuff you all are doing. And I know so many people who love Great Expectations. So I know that you are doing something right over there. congratulations on that. And I'll be waiting for that LinkedIn request to go through now.
Absolutely.
Oh, that sounded like a yeah, maybe later. Next
No,
time.
absolutely. Yes. I will go look for it. Thank you.
That
Thank
sounded
you.
like a I'm okay. See you later, dude. I'm out of here. But thanks again, man. It was cool. Very cool. And hopefully
Yeah,
we
my
can get you
pleasure.
on the MLOps community also to talk about great expectations. So moving on. We've got the last one. All good things must come to an end. And our last speaker is actually in Europe right now. And he is from Shopify. I got to talk to him before this event about Shopify and what they're doing when it comes to machine learning and how they're using Feast and how they're actually just using different tools like Airflow and having to customize them for the certain amount of scale that they have. Matt Delacour is going to be up next, and this is pretty cool. I'm excited to talk to Matt more. If anyone wants to see the pre-interview that I did with Matt, we'll post that in the chat. Also, this is it though. Last one, and then I'm going to wrap it up. I'm going to give away more swag. And if you have not filled out that MLOps community form, fill that out because there's some funny questions on there that you can give answers to and potentially win some swag. And also, I think that's it for now. We'll wrap up the whole thing in 10 minutes when this finishes and we're done with the next talk. So I'm going to hand it over to Matt, and here we go.
Thank you, Dimitri, for this introduction. And so, hi, everyone. I'm your closing session today. I'm Matt. I'm a senior data engineer on the machine learning team at Shopify. And today I'm going to talk about how Shopify helped in scaling fees for BigQuery. So first, I'm going to give you some context about Shopify and a use case we use to onboard with fees. Then I'm going to talk about 4 problems and their solutions. This will go from window functions to SKU join. And at the end of a quick conclusion. So let's jump into it. Shopify is active in the OSS ecosystem, the open source software ecosystem. In the data org, for example, we are users and contributors of Ray, Presto, dbt, Iceberg, just to name a few. We process terabytes of data. Every day, we have dozens of engineers working on machine learning problems. So all the problems we encountered and the solutions we put in place are tailored to tackle such a scale. Of course, the entire community can now benefit from it. We decided to go with Feast for multiple reasons. First is plug and play, and so we could create our custom provider as well as online store. And Feast helped us in handling the business logic like point in time, join, doing historical retrieval of features. Second, it's open source, and this is the kind of project we like to collaborate with. Last but not least, we had a great fit with William and the team, and we felt that we could collaborate with them to make Feast better in the long run. Our first experience with Feast was really successful on the toy data sets until we tried on a real use case. So let me present you this use case. It's composed of 4 feature views and 2 entities. The relationship between drivers and rides, the 2 entities, is one-to-many, which is very important for the rest of the talk. So for example, we can see that feature view A and B are about 3.5 billion unique rides, and feature view C, for example, is about 1.1 billion unique drivers. When we need to perform historical retrieval, we often only needed to do it on a subset of the data. So for example, here, 100 million unique rides. The reason is like we don't need to train our machine learning model on all the data. And last but not least, the last thing important to understand is like those 4 feature views add up to 15 features. So if we recap, this use case is about 2 entities, 4 feature views, 15 features, and billions of rows to process. So when we tried this with our use case for the first time, we ended up with many scaling issues and this type of errors, so out of memory errors. So let's walk into 4 of the problems we had and their solutions. The first problem was around how we were generating a unique identifier. So Feast needs to create a unique identifier of the rows of the entity data frame. And that was using row number over, which is window function. The problem is when you use a window function without a partition by, it means that you send all the data to a given worker. So the solution here was to compute our own UUID using like just a concat function. Here, but by concatenating all the columns that make a row unique, like the entity keys and the timestamp columns, we can retrieve the information at scale. Indeed, to perform this operation, we only need to be aware of the data of a given row. Because this entity data frame is a CTE used in many places, we need to have a function that is deterministic, as it might be computed at different places at different times. The second problem was a very small one, but basically we were outputting the results into a pandas data frame. As I'm sure you are all aware, pandas is in memory, and therefore we ended up with like a error. The solution here was simply to create a method to save the result of an historical retrieval directly in BigQuery. The third problem was a bit tricky, but basically we were performing historical retrieval on all the data whatsoever. So here, first, before we're performing historical retrieval on each feature view and then join the data back to the entity data frame, which means that if you only need a sample of your data, let's say an entity data frame containing 10 drivers, you will still end up performing the historical retrieval of all the data for each feature view. So as you might guess, the solution here is to do the other way around, to join the feature view to the entity data frame as early as possible. By doing so, on our use case, we ended up with consuming half of the resources than before. And last but not least, this problem is about like understanding your offline storage is very important. So BigQuery will optimize the query for you. It's important to understand where the heavy operations like join, group by, window functions happen. So for example, this is how our historical retrieval operation on our use case got interpreted by BigQuery. It ends up being pretty complex, right? So what we can notice is that the entity data frame is used all over the place and multiple times. Second, we could identify our 4 feature views in the red box here. What they have in common is that they are used 3 different times for join operations. And sometimes this join operation is directly with the entity data frame. So the problem we have with our use case is what happens when there are multiple entities that have a one-to-many relationship. Let's take again this example of drivers and rides. A driver can have multiple rides, let's say up to millions of them. We can see that the entity data frame is going to contain information about the more granular of the feature view. So here it will be about a ride, which means that a driver is going to be repeated over and over. So when we join the entity data frame with the feature views, there is no consequence for the ride feature view, but there is a huge consequence for the driver feature view. And because here in this example, driver 1 is completely overrepresented, this is what we call a skewed join. With this like tiny example, that will not be a problem, but at scale, that just can't run. So the solution is to pre-aggregate the entity data frame for each feature view before we join it. We can see, for example, on the left that the entity data frame for driver feature view completely shrink and only contain what's necessary, information about driver ID 1 and 2. On the right, it actually did not change much. We just dropped the driver ID column and then we perform a normal join with the right feature view. This fix is not available in Feast yet. It has been like pushed on the Shopify side, and now we are like trying to make it happen upstream. So because this fix has not been published in FIST yet, how do we use it? Well, first, we have our own API using FIST. This is for two reasons. First, part of the implementation is really Shopify specific. Like we have our custom provider, custom online store. Second, we can manage the entire experience of our users much better. And then when we have this kind of issue, we can just like unblock our users and give feedback to FIST, the developers and the community. So for example, as the time of speaking, there is a PR up, but this is a draft PR, and we still need to work on it to make it happen on the FIST repo. So let's jump to the conclusion. Because of the scale of Shopify, we could make historical retrieval using BigQuery scale to billions of records. Of course, the entire community can benefit from the work. But the real conclusion is don't be shy and contribute too. The core maintainers, like Willem and the team, are really receptive to ideas and contribution. And moreover, if you want to partner on a specific project, feel free to just reach out and other people might be interested to collaborate. On our side, what's next? We are really interested on end-demand transformation. So the ability to perform transformation during retrieval operation. So there is an RFC up that I contributed with Willem. Then we are really also interested in creating a Presto Iceberg offline store instead of using BigQuery. So if you are interested by this project, we could definitely collaborate together. So thanks for listening. I'm Madhurako. You can ping me if necessary. Also, you can just ask your questions in the Apply conference channel. Thank you, everyone. And Dimitri, just take it over.
Thanks, Matt. That's awesome, man. I am sad to say that is what we've got for the day. But I get one last moment of glory in giving away some swag. I'm not going to share my screen this time because we all know how that went last time. For those of you that stuck around, thank you for hanging out for this whole time. I am going to start naming some names. Please reach out to me in Slack if you want to claim your swag. For the most creative song lyric recommendation, that goes to Candida Rodriguez, who asked me to sing about goats probably 3 or 4 times. And you win some swag for that creative song lyric. All right. We got another Applied Selfie Award going to Cody Lynn. Congratulations, Cody. You know how to get some swag. Just talk good things about me, and that is your instant into getting swag. Next up, I just saw some great questions coming through Slack. One was from Michael Yahaya. Please forgive me if I said that name wrong. You had a great question, and I want to give you some swag. So that is it. Second to last one is How Shu. Please, again, forgive me if I say that wrong. HAOXU. That is swag-worthy. That name itself is swag-worthy. And last but not least, we've got Arnie West, who wins some swag. So all of you, please reach out to me, direct message me on Slack to get your swag. The rest of the swag that we're giving out, because we had a bunch that we're going to be giving out, and we weren't able to give it all out right now. For those people that fill out the form, the MLOps form, we are going to be selecting 10 people at random to win some swag from that form. So fill it out. Tell us your stories. There's a great one for the Have You Ever Had a Model Gone Rogue story, as we saw earlier. That is an awesome one to tell us about your failures and how you failed. And then we're going to be sharing them with the community in the next couple of days on Slack. And so it's a great way to fail in public and hopefully teach us why we don't have to repeat your same mistakes. That is all for today. We do have a feedback form too. I know we're demanding so many forms to be filled out by you, but our feedback form is just to know how we're doing. Let us know if there's anything you would have liked to have seen done better, and it's completely anonymous. So I will take no hard feelings if you say you would like a different MC next time. Last but not least, I have to say this before we finish because it was stipulated in the contract. Tekton is hiring. They wanted me to say that or else I wouldn't get paid. So go and apply for a job at Tekton if you feel the need to. That's all we got for today, everyone. Thanks for joining. Hopefully it was great and you learned a lot. We'll see you all later.